first we will talk about the paste backfilling. So in the paste backfilling, we having like percentage of solid somewhere around 78 to 85%. So the solid percentage is very high and water is very less in the paste backfilling. So what is the advantage of the paste backfilling? We can use fine particle as well as coarse particle both. We can use, and as is the water percentage is very less, so the water that remain inside the paste filling, we do not require to drain it out, because that water will be used in the hydration process. That water can be used, so no need to drain out the water like in the hydraulic filling. In the hydraulic filling is like we require coarser particle. We cannot use the fine particle due to their permeability issue. So in the hydraulic filling, we having the percentage of solid somewhere around 60%, and the remaining is 40% remain the water. And in this hydraulic filling, we are using coarser particle. We cannot use the fine particle. So we cannot use the whole tailing that we are getting. So we have to slime the tailing, and we have to utilize only the coarser particle in the hydrofill. So in that, we need to drain the water, excessive water that is there. So we have to drain the water. So as water is more, so it's required more time to consolidate, more time required for the consolidation. But in the paste fill, the water percentage is very less, so we does not require water to drain out. So the water remain inside that. It will be used in the hydration process. The water will be used. Then we will talk about the cemented rock fill. So one of our mine, Kayad mine, we are using the CRF method. So CRF method is simply whatever the rock is there, we just crush the rock and we are mixing with the cement, and then we use in the void as a backfilling. It is known as the CRF. So basically in SK mine we are using the paste backfilling. So we will discuss today more about the paste backfilling. So as I already earlier told that, so what is the CPB? Cemented paste backfill. It is a combination of mine tailing, the binder, and water. So we have three components there. One is the tailing. So mine tailing we are using. So we are using 77 to 78% of percentage of solid as a tailing. Then we are using the binder. So we are using two types of binder: cement, OPC cement, as well as the fly ash. We are also using the fly ash as a binder in the cemented paste filling, and we are using the combination of water. We making the mine backfilling as a paste. So what is the advantage? As I earlier told, higher strength can be achieved. Drainage of water is not a big issue, and like in some cases we can utilize complete tailing. We do not require like coarser particle. We do not require finer particle. We can utilize whole mine tailing in paste backfilling in some cases, as it is gain earlier strength than the paste backfilling. So the stop cycle will be reduced. Like we are low porosity is there, so we can gaining the strength very high. Some disadvantage, it's not like the disadvantage. One, like we can say the drawback is there. So like it required a higher capital cost to install the paste fill plant, for running cost as well as installation cost. Both cost is very high. For if we talk about the paste backfilling, this is one drawback is there. And it is like in most of case we cannot use like the gravity fill. Sometimes we required a separate PD pump, positive displacement pump, so that they can pressurize the filling, so that we can send the filling at very horizontal length. We can increase the horizontal length of flow with help of PD pump. So here is a flow diagram how backfill material is getting prepared. So we having tailing concentration in means whatever tailing that generating after the milling process, in that we having somewhere around 45% solid. So we having thickener. So thickener we are adding the flocculant in that. So after that adding of flocculant in the thickener, we having increased the percentage solid from 45 to 70%. Then that solid we are using in the filtration plant. There with the help of disc filter we are increasing the percentage solid from 70 to 84%. Then we having a mixer. in which 84% solid mixing with the cement. We are adding the cement as well as fly ash as a binder, and after the final product when will come, so the 77 to somewhere 80% of total solid will be there, and then we are distributing in the underground mines. So, like this is again a process flow diagram of the paste fill. So this is the mill tailing. So this is deep cone thickener. So whatever the tailing generated from the mill process, we are sending in the deep cone thickener. So in the deep cone thickener, we are adding the flocculant in that. So whatever the after the whatever the particle that has been settled down, so we are sending it to FFT, filter feed tank. Then somewhere around 45 to 70% solid, because that 40% solid has been solidified, and now the solid percentage has been increased to 70%. Then we are sending this to FFT tank. Then we having disc filter. So from that 70% solid, increase here somewhere 84% solid. So here it will be like very cake type things will be there. So here cake conveyor is there. So 84% solid, we from the cake conveyor we are sending in the mixer, and then we are adding the water which was the overflow from the deep cone thickener. We are sending in the mixer, and here we have the cement silo. So in the mixer we are mixing the percentage solid like the mill tailing, the water and the cement. So final product after the mixing we are sending into the hopper, and then we having two paste plant. One paste plant is running by the gravity, as gravity play a vital role to transport the mill tailing and the backfilling, and one plant we having the PD pump. So like in that plant we having the horizontal length is very high, so we have to pump the paste fill to a certain length. So we are using the PD pump, and in the one plant we are using the gravity to flow the paste fill. So here is some picture of cement silo. This is like deep cone thickener. This is disc filter where we are making 70% solid to 84% solid. And this is the photograph of cement feeding system. We having a one control room where all the data, moisture content we are maintaining. So this is a photo of control room, and this is the photo of underground reticulation system. So you can see that kind of pipe. This is the paste which is going inside the open stove. So it is the underground reticulation system that I have shown you. So this is one example of stove, how we are filling. So it was the stove, and this is the blasting boundary. After we are making it void, and we are preparing one barricade here. So we are having two types of barricade. One is 500 mm thick M35 shortcut barricade, and one is that is bund barricade, which is like a combination of waste plus shortcut. So we have two types of barricade is there. Once we are making the barricade, we are filling a higher percentage, 10% cement in the plug. It is known as the plug. So we are up to 9-meter height, we are sending higher percentage of cement. So we are making a plug. Once the plug will be settled down after 48 hours, when the plug has been completely cured, so then whatever the bulk filling or main filling that we are putting, it is not pressurize the barricade, because the plug has been settled down. So no more pressure is coming onto the barricade. Whatever pressure is coming, it is coming on the plug fill. So this is the line diagram of like how we are making. We having the pipeline up to here, and we are sending the paste fill here. You can see after like 48 hours, we can send a 21-ton LHD over the cemented paste fill. It will be like a solid ground like this. After 48 hours, we can send a big machines over that. So it required a very disciplined manner to fill the void into that. So for that we are using CMS. So before to planning anything, we have to make a pour plan. Pour plan is a plan where we are how much meter cube of volume we are going to put, what will be our process flow diagram, because it required huge cost to laying the paste fill line. If a paste fill line choke, it gonna impact huge cost to the company. So it required a very disciplined manner. For that, we are making the pour plan. So in the pour plan, we are determining what will be our underground distribution system, material, pipe, slump height. We have lots of measurement is there. First, we are taking all the measure, then we are sending the paste fill into the mines. So like you can see in our mine, one thing is the CMS, cavity monitoring scan. So CMS is simply, it is infrareding lots of rays and that got reflect back, and we are getting a profile of a open stope. So once we are getting a profile of open stope, so that we can know up to a height of 9 meter, we are making a plug, so that we can know with help of CMS how much meter cube volume come in the plug, how much meter cube volume come in the bulk, and what is the position of stope. So you can see this is one stope we are making the Rhino. So we having data mine, Rhino, flag 3, lots of software is there. With help of Rhino and data mine, we are using the CMS volume in that, so that with the help of that, we can estimate whatever volume will come in plug. So we are, suppose that for, if we will take this example of this 255 S240 stop, so we will send 2000 meter cube volume in plug, then we will wait for 48 hours, and then we will send 6300 meter cube in the bulk filling. In the bulk filling, we are using less percentage of cement compared to the plug, because whatever pressure is come of the bulk fill, it's come on the plug, not on the barricade. This is one example of one sheet that we are preparing. So in that, all kind of safety measures is the pour, non-routine, tight filling required, bezier pipe is there, diamond drilling hole required not. This is all the safety measures we are taking before sending the filling into the underground. So one major thing which come after, like flow model. Suppose that we are sending the paste fill with help of gravity, and if the process flow diagram is not accurate, that flow of paste fill will become choke and whole pipeline. And we here somewhere in the mine, 18-kilometer pipeline is there of the paste fill. So it is very, the flow model play a very vital role, very important role to calculate either this flow will go to the last pouring point or not. So this is with the help of like friction, like friction force, what will the friction losses will be there. So with the help of that, we are calculating, is that, suppose that we are sending from paste plant, which is somewhere around 512 MRL, and we are sending somewhere like 1 kilometer below from the surface. So does that flow will go to that area or not? For that, we required flow model into the mine. And now we will talk about our mining method at SK mine. So this is one layout of like sub-level stopping method. So during the primary stop, so this one and this one, they all are the primary stop. So during primary stop, we having solo machine, solo DL421. This is one machine that can drill up to like 50-meter deep hole, and diameter can drill 105 meter to 115 to 165 diameter that can drill. So with the help of that solo machine, we are drilling holes from above level to down level, and then we are used with the help of blasting. We are exploding the area, and then with the help of LHD. So at SK mine, we having two kinds of LHD. One is 17-tonner LHD and one is 21-tonner LHD. So in underground, we have like huge beast running in the mine, which is taking 21 ton in one go. So these are the big machine. So as we have to hold 6 million ton, that is a big volume. So that's why with the help of, we have the combination of 21 ton LHD to 65 ton dumper in the mine. So with the help of this LHD have a remote. So, and also we can operate that LHD from the surface. So what will be the dream of a mining engineer? Like no one will work in underground. So it is happening in mine. So we have tele-remote operation. So one person sitting in the AC room and can operate the LHD, which is running in a like a very hot environment and in a very dangerous environment. So we have two types of tele-remote operation. One tele-remote operation is one surface is sitting, one person is sitting on the surface and operating the LHD from the underground. And second thing is there, the remote LHD. So what is remote LHD? Like person standing somewhere in the safe area, and with help of, like when we are playing the video game, with help of like the remote, he is using his bogger to go into the dangerous area, open stop area, and doing the mucking. So this is the concept of remote LHD. So after the complete mine of this primary stop, we are backfilling the primary stop with help of paste filling. And after the after the primary backfill, we are going to mine the secondary stop. So with help of paste filling, we can recover secondary stop, which is known as rib in the, also known as the rib in the coal mine and some metal mines. So we can excavate the secondary stopes. So with the help of paste filling, we can increase our recovery. We can take everything out. We can take the crown pillar, we can take the rib pillar. So no need to left the precious ore that has been given by the god to us. So we can excavate all things, the primary stop as well as the secondary stop. So once the primary stop has been mined out, we will backfill. So after the backfilling, it will sustain a vertical height of somewhere 115 meter in our mines. So you can see, imagine a height of 115 meter long vertical height, somewhere around 50 meter of paste fill still remains sustained there. But now we have reduced the stope size, so we having 30 meter stope height. So 25 to 30 meter stope height, that paste will remain sustained in a standing wall. That will provide, that will work at a side wall. So we can excavate the secondary stope by this method. Yes, sir. Yes, yes, drop point. Yes, 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 yes. That's yes, sir. That will come underhand mining. So my topic of this today is underhand mining. So, and as I earlier mentioned, we have two types of mining method. One is sub-level stopping with backfilling that I explained, and one is underhand mining. The below part, how we are going to mine, that will come in the next slides. Yes, sir. Yes, sir. I will come to the in the upcoming slides. हाँ सर, 30 मीटर, हाँ हाँ। नहीं सर, वो बेरे पिलर हम नहीं छोड़ते हैं, वही पिलर हम नहीं छोड़ते हैं। वो जो आप सिल पिलर की बात कर रहे हैं सर, अभी आपने उसको पूरा भर दिया, अब हम नेक्स्ट हम पेस्ट फिल में ड्राइव मारते हैं, then we are making a drive inside the paste fill. So we are not leaving any kind of barrier or seal pillar. So we are making a drive inside the paste fill. Paste fill में डेवलपमेंट करते हैं सर। हाँ। इसके छोड़ते हैं। हाँ। और खोलते हैं। माइन करते हैं सर। टॉप डाउन मेथड है सर, वो एक्सप्लेन करूंगा आगे। So this is one again example of, like suppose that this is the primary stop, this is the primary stop. So once the primary stop has been mined out, we are backfilling the primary stop and we are making the secondary stop. This is the same photo, which one earlier has the 3D picture. This is the plan and section picture. And now we will talk about the underhand mining. As sir saying, how we are recovering, how we are going down inside that. So sir, suppose that sir, this is my backfill area. So first we are doing development inside the paste fill. So you can see this drive. So this drive we are making in the paste fill. For that we required certain amount of strength of the paste fill. So good thing is there, Suppose that what is the biggest hazard in mines? That is the rockfall hazard. But because why that rockfall hazard is so much dangerous? Because rock is non-homogeneous. It is elastoplastic capacity is there. It's not elastic. But in the paste, it's completely homogeneous mass is there. It is elastic material. It is like child material, continuous, homogeneous, elastic material is there. So, like you are sitting in the room on the basis of what? We know that how much strength that pillar is gaining, how much strength that beam are gaining. Because we are, no, it's like homogeneous material. This beam is homogeneous. So we know that what is the strength is there. But in the rock, we having discontinuity. But good thing is there in the paste. Paste is homogeneous, elastic material. So we know the property of the paste. It is like cement block. We can development inside the paste drive and then making a drive inside the paste fill. Once this drive will be done, then we are doing drilling inside the bottom area and then again mining below that. So this is underhand mining. So currently underhand mining is practicing only in two mines of India. One is the Rampura Gocha and one is the Sindesar Khurd mine. Yes. Sindesar Khurd, which I am SK mine. Sir, yes, good thing is that like exposure time, more important is, sir, hydraulic radius. How much exposure area we required. So till now, we are exposing 500 meter square area. Like we having 20 meter strike length. So we are excavating 25 meter ore body width. 25 into 20 meter. So that much area exposed, we are exposing up to 4 months and 5 months. Still it's remain intact. Yeah, 5 by 5. But sir, once we are doing mining, so entire stope has been exposed. Yes, short kit and split set, sir. Yes, sir. No, no, sir. We have to put short kit and split set and again short kit. So somewhere around 100 layer of short kit will there, sir. First layer of 50 short kit, we are putting split set, then again 50 of total 100 short kit will be there, sir. So this is underhand mining, an example of underhand mining. And now important thing is why we require underhand mining. So it is one lithostructural model of our mine, which we have prepared in Leapfrog. Leapfrog is a software in which we can make our lithostructural model. So you can see how much complexity is there in the our mine. So this is our mine, and this is the area. You can see complex folding is there. Like, sir, actually we having like two things there. One is the core logging data, and second is the underground mapping, sir. So we, like I am a head geotech, I have one team below that. So they are doing regular mapping, and in the help of leave underground excavation, sir. With the help of exploration boreholes as well as from the underground mapping, sir. Like when we have exposure of 5 by 5, we are doing the mapping with help of Bantan compass, and we are taking data and we are projecting the fault upper level to another level. So you can see how much big fault. So imagine this is from here to here, it is 1 kilometer. So how much big structure is running? Like 1 kilometer big fault running into the mine, which is creating the complexity. So whenever we are going the overhand mining, due to that fault area, whenever we encountering any fault area, it started caving. It started caving because we having a fault area and it is under high stress. So it is started his profile losing. To mitigate that, we have started the underhand mining. Now in the roof, we having the cemented paste fill, which is very elastic. So the in the deep mine, where the, like suppose that this is over LVS of SK mine. So from surface to somewhere around 1 kilometer below. So now stresses is very high. We cannot go with the overhand mining because the stresses are induced caving is happening due to the stresses and due to the faulting and folding, due to the complexity of structure and due to the complexity of stresses, the strata is behaving self-caving. To prevent that, we have started the underhand mining. So now, as in the roof, we have the cemented paste fill, and it is very elastic. So it is not cave, it is sustained in a very good manner. So now with the help of John Lewis sir and like back engineering and over also in-house modeling, we started like how much strength we required, to go inside development. Like sir is asking how we are doing development inside the paste field. So before going development inside the paste field, we required certain strength. Once we achieve 780 kilopascal, like 0.780 megapascal strength of paste, so that it is a safe strength to go and can develop inside the paste field. Sorry, we are getting 1.5 MPa somewhere, 2 MPa after 28 days. Like yeah, sir. So after 28 days of paste fill, when plug has been cured, when we will wait for 28 days, and then we are going to do development inside the paste fill. Yes, 1.5. It is like given by John Lewis sir himself. So and then yes, sir. That is enough, sir. If we will give more strength, then again issue will be caving. Because sir, if it will having more strength, 100 MPa, somewhere around 100 MPa, so sir, it will again start caving due to their stresses. Yes, sir, 0.78 MPa. It's like very required strength. 2 MPa somewhere around. Somewhere 2 MPa. 2 MPa, sir. So now for excavating a 5 by 5 meter opening, we required 780 MPa. Sorry, 780 kilopascal. But for exposing a huge area, 500 meter square area, we required somewhere around 1 MPa. But with the help of 1.5 factor of safety, we have increased up to 1.5 MPa. So this is one example, again one example. So it was the paste fill stove we have developed inside the paste fill, and we are doing mining with the paste fill. So you can see this is the paste and this is the paste drive. It's completely like no loss in the profiling. It's completely 5 by 5 circular profile is there. So it is the drive that we have developed inside the paste fill, and this is the profile. Profile is still remain there. We having a void created below that, and you can see the roof is still intact. The paste fill roof is still intact, and now we again backfill the area, the below area. So this process is continuously, and we are going down, 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 down this method. So till now, somewhere around like 40 to 50 stops we have mined out. But in Rampura Gocha, we have around somewhere around 600 stops. Till now we have mined out and in very safe manner. Sir, we having hangwall quartz mica schist, and strength is somewhere around 130 megapascal. 130 megapascal. But sir, again, if some hangwall still fail, so we have the remote loader, sir. No one have to go inside the open stop area. It remotely we are operating, and we are something fall, it will happen on the LHD itself. No person will be in danger. Paste, sir. Till now we don't have any fail in the paste, sir. Paste, like we have one football drive in the paste, which is running from last 5 years. No, sir, no much influence in that area. Because sir, paste, the good thing of the paste is elasticity. It's very elastic. It's like rubber. It observes everything. Whatever shock wave it will observe. Yes, sir. One of our colleague, Ashish, did some study in that area. Then, sir, like your point is right. So, what we can say, like two remote loader in a 2 year time period. But it also, sir, we can recover, sir, with help of again one loader. With help of one loader, we having one tie arrangement. It will plug on to the balancing mass of the. Yes, it is there, sir, but it is not that much effective. Like you are saying, it is not that much effective. Dust is there, dust environment is there. It is not that much effective. But with help of like cable tie arrangement is there. With help of that tie, we can. Sir, for the secondary blasting, we are not doing secondary blasting, sir. We are doing secondary braking. We having one rammer machine that is also remote control operated. So we are sending the remote control loader into the mine and it is breaking down rock breaker. So like for the safety front, sir, Hindustan Zinc give huge cost and like huge R&D we did. Now we have completely eliminated the secondary blasting in the mine. So we are doing secondary braking into that. करते हैं सर शॉर्ट किट बोला ना शॉर्ट किट स्प्लिट सेट वायर मेश एंड शॉर्ट किट सर sir bolting will not be done because sir whenever we are start dealing with water it becomes slurry. Yes, friction support sir, friction support yes. It's like dia of the hole is somewhere 38 sir, and we are sending 47 that split set into that, so it is expanded, so it is giving confinement to the side wall. Now we will discuss some about yes. Cost decline 21 none. No sir, we are yes sir to produce. Remove. Like sir, big. Five hundred deep. Then because sir, if you want to send some big loader LPDT, we require big size of dimension. Yes sir, 65 ton. प्राइमरी सेकेंडरी मैटर नहीं करता है फिर पेस्ट फिल मैटर करता है रोक अपने यहाँ कहीं है ही नहीं सीमेंटेड पेस्ट मैं कंटिन्यू सर डन सर सर yes yes now we can start with like the instrumentation part. Guys please attention, it can be like helpful to you too. So what kind of ground control instruments we are using in the mine, we will discuss about it. Like why we required ground control instrumentation, like we need to know the behavior of the strata, we need to know how rock mass is behaving. For that we required ground control instrumentation. As in SK mine we are doing back calculation. Suppose that we are putting some stress cell and we expecting a change in stress somewhere around like 2 MPa. So and with help of instrumentation we are getting 4 MPa. So we are doing recalibration and we are sending feedback to John sir also. Sir also doing the recalibration. So for recalibration is one of the most important factor in the design part. Like in most of the mine, I can say, as I am a head geotech, so I can say in most of the mine, recalibration is not happening. Recalibration is one of the must required things for a model. Suppose that if you are doing modeling and you expecting a hang wall deformation up to 2 meter. So if you have installed a MPBX in the hanging wall and we are getting the exact same numbers of deformation, so we can say that the data that we have taken in the design is right. Otherwise, either we are conservative, either we are more less like more safe towards safety. So the calibration is one of the important factor, and the calibration we can take with help of instrumentation only. So today we will discuss about what kind of instrumentation we have in our SK mine, like MPBX, digital inclinometer, tilt meter, stress cell, EPC, instrumentation bolt, TEL10, and then we will talk about monitoring system. We having CMS, we have RFID tag system, and one is the seismic monitoring system. As we are working at a 1.2 kilometer below, we have a huge seismicity. To get that data, we required seismic monitoring system in the mine. So first we will talk about the MPBX. So most of the people how MPBX work, but still I am explaining with the figure. Suppose that this is our hanging wall. So whenever in the ore body we have one hanging wall, we have one foot wall. So hang wall have tendency failure toward the open stope. So we having one like drive known as the exploration drive. From where we are doing exploration, from that drive we are putting long hole, and in the same hole we are putting MPBX with different depth, like somewhere 25, 24, 22. It's like that. If any deformation started happening in the hanging wall, like only in the first anchor movement is there, so we can say the failure is very limited up to only the first anchor. If all the anchor having movement, so we can say mass movement is there, whole stope gonna collapse. So that kind of data we can get from the MPBX. Like you can say this is a mechanical MPBX, like we are drilling, we are putting anchor on that, then we are installing head over that. So this is one example that I told you. Like this is the movement of only first anchor. This is the movement of second anchor. If all the anchor have movement, means a big mass is going to move toward the free face. Big failure can be there. So this is one example of over one stope where we having some little failure was there. So we are very well predicted that failure can be there with help of instrumentation. Like nowadays, digital MPBX is there. It is not a good approach to go in the hanging wall and measure the deformation, because hanging wall itself always having the tendency to move toward the open free face. So nowadays we have installing digital MPBX. So everything is mechanical, but the head is digital. With the help of Geocon digital MPBX, we are installing the digital MPBX and we are taking the data on the surface. So MPBX data we are getting on the surface with help of digital MPBX. Multi-point borehole extension meter. So now, like sir, if you talk about the RMR, sir, so in the hanging wall we having like fair range 40 to 60. Yes, in the ore body good, like 60 above 60, but in the foot wall again like less tensor is there. So like as I told, one complexity is there in the mine. Like you can see, this is one dipping of the ore body. So earlier dipping of the over SK mine deposition happening along a fold. So you can see earlier dipping toward western, now dipping toward east. So due to that complexity, our shaft is somewhere in the hanging wall. So we have to put lots of structure. Like this is one example, 3D example of instrumentation that we are doing in our mine. So you can see the all the magenta color, it is the stope that has been mined out and backfill. All the green color, it is the future stopes, and all the blue one is the running stope. So you can see we have even hang wall drive, and we are going to put long MPBX over that, and then we can get the data from the hanging wall. Digital MPBX is there, and this is one digital inclinometer. So in the shaft we are putting 2 borehole, and in that borehole we are sending this inclinometer. If any deflection happening, into the shaft, we can get the data from the inclinometer. And this is like tilt meter. So this tilt meter is working on a radio frequency program. So it does not require any wire to snitch. So we are going to put this tilt meter in our shaft area. So how this tilt meter works? So if suppose that this is a bench of open cast bench, if any movement started happening in the open cast bench, we can get the tilt data. So we are going to install this tilt meter in our shaft from 65 mRL to somewhere around half kilometer. We are going to put this tilt meter in our shaft. Like then the stress meter. So this is suppose that the primary stop is there. So as I earlier told, the recalibration of the data is very required. So suppose that we are doing some modeling and we are expecting some change in stress. To measure that change in stress is within the limit or outside the limit, we are going to install this stress cell. So if due to the excessive stresses, the rock whole got collapse, whole got deform, and that deformation with help of the like it is making by the steel having some different modulus of elasticity, and this is the rock surrounding rock having different elasticity. But if the rock got deformed, that stress cell also gonna put pressure over that, and that change in stress we can get with the help of the stress cell. Its reading also coming on the surface at SK mine. Like you can see, like gradually the stress cell is in very like negative reading was there, and when we started the blasting, so sudden change in stress started happening into the mine. Like as I told that for the barricade pressure, we have to measure the barricade pressure. So we are going to install EPC, earth pressure shell, on the barricade to get the pressure, what is the exact pressure is on the barricade. So this is the EPC photograph we are going to put on the barricade and going to take the reading. So not now, sir. Piezometer we are installing, like I told, sir, in the paste field we do not have, sir. We have hydrophil, we have dismantled, sir. Sir, has been dismantled. The plant has been dismantled last 2 years ago. So we have completely shifted in the paste field. So in the paste field, we do not have an issue of the water. So we are not installing the piezometer. But in the tailing dam, we have one tailing dam, huge capacity tailing dam is there. There we are installing this piezometer, sir. But this EPC, we are installing on the barricades. So at the time of plug filling, so it's continuously increasing. Once plug fill has been cured, it's little bit decreased, but it's never going to attain again 0. This is instrumented bolt. Like it required some time of modeling how instrument bolts work. This is a telltale. Everyone knows from the like coal mines how telltale is going to reform. In the paste, we having one cold joint above that. The cold joint is the joint which is making between plug fill and the bulk fill. Like as I told, we are making the plug filling, and after 48 hours, we started the back filling. So there is a cold joint which form after the time gap between the plug and the bulk filling, and as well as change in cement percentage. In the plug we have higher cement, in the bulk we have less cement. So it is a cold joint formation. To get the deformation, is really deformation happening in the cold joint or not? We are putting this telltale. So we are installing the telltale 10 meter long hole, and we installing telltale. If any deformation happen, we can get the data through telltale. Yes, sir. No, sir. Till now we don't zero. Yes. And this is one example of CMS. As I told, this is the monitoring system. I think that can be adopted by every mines. It is giving the complete profiling of the stope. We can do reconciliation. Suppose that a blasting engineer plan 10 rings. Is that 10 ring blasted properly or not? Is there any ore left? Is there any ore break is there or not? With help of CMS cavity monitoring scan, we can get the profiling of that. So it's a camera is there. It is distributing lots of rays, and that rays get reflected back to the camera, and it give us the profile like this. So you can see the green one is the plant blasting boundary, and the blue one is the blasting profile after the blasting, what profile we get. So you can see this was my plan, and we have left some ore here and some ore here. So with the help of CMS, we can get complete detail of what is going inside a open stope. Sir, somewhere around 1 year. Like like 25 lakh and then processing fee, something like this. So now yes, 70 lakh. Somewhere 1 year. Mota mota. So sir, digital MPPX, everything is mechanical. Only the head is digital, sir. So the cost of one digital MPPX is 2 lakhs, sir. Yes, sir. Yes, everything. Every device is mechanical, sir. Yes, yes, sir. With the help of, yes, sir. So as as I told that shaft is in the hanging wall. So for if any movement happen the button, so button, the shaft, everything is running on the button. So it is very critical role if any deformation happen the button. So we have put this RFID on the shaft button system, and with the help of data logger, it is going upside. If any movement happening into buttons, we can get the data with help of RFID tag. This is the RFID tag we are going to put on the buttons, and this is like skip. We are putting data logger. Whenever this that come in contact, we can see the real profiling of the buttons. And this is the real-time monitoring. This is like one system of Geocon. We having 64 channels data logger to data logger. So in single data logger, we can put numbers of sensor. So MPBX, trace cell, EPC, all we can connect to the data logger, and we can get the reading on surface. And now we will talk about seismic monitoring. Like seismic monitoring system is like IMS is there, instrument mines survey system is there, which is giving us the triaxial geophone is there, and its location is there in the mine. So you can see like 1, 2, 3, 4, 5, 6 number of sensor is there, which has been installed in the mine, and it is making a loop. Every geophone is connected to each others. So if any seismic event happen in the mine, we can get their location, and we have trigger action response plan according to that. We have make the like you can see, if any event happen, we can get the coordinate where the real event happen, and we can do the mapping, we can do the damage mapping, we can do the inspection. If any damage is there, we can withdraw the manpower according to that. So with help of this seismic monitoring system, we are implementing the TARP. Sir, 300-meter ideally. One sensor range is 300-meter. So it is array of numbers of sensor. Sorry, sir. Yes, it is capturing every blast reading, sir. If any blast is happening, we are getting the reading. Yes, sir. We have TARP, trigger action response plan. Yes, sir. Developed, and we are implementing. Yes, sir. Like, sir, uh, not in this slide. Yes, sir. Yes, sir. So let me tell you, sir. Like if any event with magnitude more than 0.5 MPa. So if any event happen in the control room of mine, we can get the coordinate. Okay, in X stop we having seismic event. So he immediately remove the manpower of surrounding areas. 0.5 m magnitude. 0.5 m event happen. So we are somewhere around like 2 stop distance. 2 stop somewhere 100-meter area we are withdrawing. If one event happen somewhere 200-meter area, we are withdrawing the manpower. Yes, sir. Above from the working active area, sir. 300-meter. Yes, sir. Confidential. Can't share. It, yes, in that, in every arrival of P wave, there is some characteristics which is different from blasting. signature is there, like sir saying. Arrival of P wave or arrival of S wave, sir can understand. That will describe is that really seismic event, or it is a blasting event, or it is a rock noise, or what is there.
They are from Hindustan, sorry, Happy Gold Mine.
Yes, that's why
So
interested.
they have reached up to 900 meters.
Yes, sir.
They are getting seismic
Seismic
shock.
event. Yes.
तो एक करोड़ का है और 1 crore का है ना
So,
1 crore देता मैंने चेंबर
thank you, sir.
अगेन
Any question? Thank you, sir.
Yeah, thank you very much, Pradeep. So this was a very interesting lecture, and I want all of you to even ask questions. ताली तो बजा दीजिए, लेकिन ask questions. There may be plenty of questions, I believe. So please write it down. We have kept a box here, query drop box. Please drop because there is not enough time. We have to move to other lectures. So in this query drop box, you can put your queries, and in the final session, we will address those queries. Okay. So Shubham, Shubham, you'll be giving now. Sir, actually, it's the continuation. So I invite Shubham Vijayvargiya. He's a mine planning expert from SK Mine. So I had already introduced him earlier. So please continue your lecture.
So, good morning all. I'm Shubham Vijayvargiya. I'm working as mine planning engineer in SK Mine. So, we will just discuss about some technology advancement in mine planning, what software we are using in mine planning and all. Yes. So, we will move forward like introduction of mine planning, then mine designing criteria, what we are using, then mine development process, what is the mine development process, what we are using, then mine design parameters, then short-term mine planning, long-term mine planning model, and then life of mine and rate of production plan. So I will just give a brief introduction about HZL. So we are India's largest lead and zinc producer. We are third largest silver producer globally. We are second largest lead zinc producer in globally, and we have world's largest underground mine in Rampur Agucha, and India's largest digital mines and synthesis coal mines. We have almost 75% market share of zinc production in India, and we have almost 25 years of mine life from today onwards. This is the introduction about SK mines. This is the longitudinal vertical section of our SK mine. As we can see, we have almost 12 lenses in our mine, among which this red color ore body you can see. This is the main ore body from where our 60 to 65 percent of production we are doing. Rest 35 production we are doing from auxiliary lenses like SK1, SK17, SK4 and all. We have almost 110 million ton reserve and resources, among which 43 is approx reserve and the rest is of in resource contribution. Starting from 1990, we have discovered our resource in 1990. We have commissioned our project in 2000. From 2000 to 2024, we have start from production start to 5.65 million ton. There was many technology advancement. Earlier we were using 7 ton LSDs, then 17 ton, then now 21 ton LSD we are using. Earlier we used to do 30 ton of trucks, then 50 ton, then now 63 ton truck we are using. So, what is mining? As we all know, with planning perspective, what is the mining? So, mining is extraction of valuable minerals safely and economically. While designing the mine, we used to take these two consideration in our top priority, like safety and economically. A mining process can be divided into these five pillars. First is initiating. Initiating lies environmental clearance, lease from government, like that. After taking lease and environmental clearance, we will plan the plan the whole process, like how much the ore body, what will be our rate of production, 5-year plan, 10-year plan, like that. After planning process, we will do the execution. Operation is start, whatever ramp, shaft, whatever we are developing. Then after establishing a complete mining process, we will uh, we will make some system to control that complete operation. Then mine closure time. So we will move forward in this PPT, in this five pillar mainly. So why do we need mine planning? There are two major reasons. So of mine planning. First is as any organization want to do maximum of their profit. So first is maximize the profitability. Second is to install confidence internally and externally. Internally means whatever we are planning, whatever project we are starting, there should be some like a limit. In 5 year I will do this much of product, in 10 years I will do this much of production. So within the team, to build a confidence we need a mind planning. And externally what is means, like in between stakeholders, who is investing in your company, you have some plan, you will show some plan that in 5 year 10 year I will move forward. So to build confidence internally and externally, we do need mind planning. There are two type of plan always. First is long term plan and then short term plan. A long term plan, we can say, is the plan for the most, for the main proportional of the ore body. Like I have saw the LVS of our mines. So in mainland 70% of the ore is lies in that mainlands. So what is planned for that 70%? That is our long term plan. Basically more than 5 year plan is used to be long term plan in our case. Short term plan is step by step plan, like monthly plan, weekly plan, 1 year plan, 5 year plan, up to 5 year plan we used to do in short term mine plan. So mining cycle of SK mine, we can divide our whole mining cycle in this six process. uh, First is development phase, where the mine planning process is 70% of our mine planning process. Then production phase. In development phase, again we can see three processes are there. First is exploration. So we have surface exploration and underground exploration. For surface exploration, we have Dyna, which can drill up to 1,000 meter. A hole can be drill up to 1,000 meter. Then further to build confidence, we have MCR and UCD for exploration purpose. We use 25 by 12.5 meter grid to build a confidence in ore body. Then after having some ore body shape, we use core logging, sampling, and assaying to know the grade what grade we have. Then based on essay model or ore body, we use we used to make one block model. From that block model we used to do stopping design. That block model used to divide into some parts. In our case we have two type of stopes in our mine. Like first is 25-meter heighted and second is 35-meter heighted. So based on that ore body model, we used to make some stope design. Then after designing a stope, I will get to know that this much of production, this much of RNR I have in our mine. According to deck, I will decide the development. What development I need. Then crosscut drive. What is the size we used to adopt? Like which jumbo will come? Like that, resource planning and designing, both part. Then after development and stope design, I will go up to production drilling blasting, then ore production and then blasting. I will explain further in next slides. So brief introduction about surface and underground exploration. So for surface and underground exploration, we are using datamine software, datamine UG and datamine RM also. So there are two type of model. First is resource model, and second is geological block model. Resource model is whatever I am getting from surface exploration. That is our resource model, which is used for long term plan. And geological block model is whatever confidence I am getting from our underground exploration. That is geological block model. So we can see these are the hole which were drilled from the surface. These hole have three type of data. First is collar, second is litho, third is survey data. Based on these three data, those holes are being plotted in datamine software. Accordingly, wherever from assay data, wherever the ore was found, a ore body shape is being formed using that borehole data. uh, the whole mine where I'm doing exploration, that can be divided into some grids. uh, like for surface exploration we are using 100 by 100 grid, and for underground exploration we are using 25 by 12.5 grid to increase the confidence level. So this is the basic process of block model formation. From that block model, two type of information we are extracting. First is geological information, second is geotechnical information. Geological information what we are getting from that block model is basically our body shape and grade distribution. In our case, grade used to vary from 2% to almost 7 to 8%. So the mineable grade is 4.5% basically. So we need to design the stope in very economically, so that I can manage my cutoff grade. So we can see this is the picture of our block model. You can see different type colors in that block model. Red color you can see is the most high grade area, where 7 to 8% of our grade lies. Second is blue colored area, that is 6 to 7%. Likewise in cyan color and pink color. So this is the block model what we are getting from that exploration data. Second is geotechnical information. So when I will do the exploration, there will be some RQD also we will analyze. In logging data also we will analyze some things. So from that, some geotechnical information also we used to get, like what is the rock type, at which depth, which rock is encountering, like what are the clay zones, what is the RQD of that particular area, is there any structure in that particular area, or like any shear we can get from that block model. After block model formation, we will come on the stope designing part. So I will just spend 2 minutes on this slide. What is a stope? A stope is like we have hanging wall and footwall, two type of ore bodies there. In between, ore body will lie. So along ore body, that is the width. What terminology we are using? Along the ore body, it will be width. Across the ore body, it will be length. Uh, Difference between top level and bottom level is stope height. So how stope used to prepared? So whatever the block model I have received from the geology, based on our production rate, our payback period, at how much time I required the ore, first truck of ore, according to that, we used to design the stope, like what height I need, I have need to do, like in our case 25 and 35 meter. So from resource model, I will do the I will cut the ore body into some like finished dimension, like in our case 20-meter width we are using, 25-meter height and 35-meter height. Then on mine design part, there are some criteria, some factors what we are using while mine designing. So variables are ore body geometry. According to ore geometry, what method we are adopting, like according to ore body shape, transverse and longitudinal, both method we are using. We have some area where ore body width is like 30 to 35, 30 to 50 meter. There at in that area, we are using transverse method. While there are some areas where like ore body width is 5 to 8 meter, where at that case we are using longitudinal method. Then grade distribution. If grade is uniform, then I will go in transverse method, and if grade is uh, like varying, then I will go to longitudinal method. Then strength of rock. uh, if strength that has RMR, in we have RMR, two type of RMR, like fair to good. In good RMR we are doing underhand mining, and in fair RMR we are doing overhand mining. Both type of mining we are using. Then ultimate mining method, there are some risk factor also. During exploration process, there will be some deviation, like there will be some deviation in holes whatever we are drilling, and that quality is a then ore body modeling and reserve estimation also. These are the some development terminology what we are using in our mind. First is capital development, and second is secondary development, or we can say revenue development. So there are two type of cost, capex and opex. So uh, that cost has major part on mine development in our case. So it is highly required that we will optimize our development. So in capital development, what is the capital development is, that is whatever development what we are doing in like on long term basis on infrastructure that has life more than 1 year, that is capital development. And every development that has life less than 1 year is revenue development. In capital development, like shaft infrastructure, footwall drive, ramps and all will come in capital development. And revenue cross cuts what we are developing, like for to reach up to the orbity, that will be revenue development. So we have two type of cost also, cost COPV1 and COPV2. In COPV1, capital development cost will not be included. In COPV2, capital development cost will be included, that will part of capex. So these are some mine design parameters. We used to design our mine in datamine software, datamine RM, datamine Studio UZ. These are some parameters what we are using. So after developing RAM, we will let me explain one by one. In decline, we have 1 in 7 decline what we are using. In decline, we have crossovers, like crossovers of minimum 15-meter length. At every 150-meter interval in decline, we use crossover to pass the vehicle and all. Then level access junction, all development from ramp, footwall drive and arc, that all are in arc shape only. Then pocket sums we are using at every 250 or 300 meter, we are providing pocket sums to develop a decline. Then passing bay, then main pass as per DGMS regulation number 95 of 1961 MMR. We are developing main passes and get in box copy also. Then again on mine design, previous slide was on, one second. Yes, previous slide was on up to ramp, up to level access, where we are reaching up to level access. What we are developing is lies in this slide. After level access, what development we are using is first is level access crosscut. This is also 5.555 arc shape design, where LPDT is our maximum size of vehicle, that is LPDT can run. Footwall drives, then waste crosscut, ore drives, level sum, shaft access, and airways shaft also. So this is the layout of our one of our level. Uh, After entering from ramp level axis, then we used to establish some mine services like power cross cut, like dewatering cross cut and all. There will be a ventilation cross cut for first, either it is intake or exhaust, whatever. So all the services will be developed in this area only. Then after developing services, we used to make a footwall drive, that used to be 30 to 40 meter from our uh, ore body contact. Then we used to develop like revenue cross cut and all. These are some software what we are using in our mine planning process. First is data mine. In data mine we have some version what we are using. First is studio UG, studio RM, studio EM, AGs for drilling blasting, EPS for scheduling. So data mine we have 5 module. In this week, now we are moving from data mine to this week. We are in transformation phase. So in test week, we have implemented already UGN, CAD and UGDB. Now further, we are going to implement scheduler, UGM, and advanced survey. For SSR design and numerical modeling, we are using Flag 3D. For structural modeling, we are using Leapfrog, and for ventilation design, we are using VentSim. Then after mine designing, as I have told, we will enter into production phase. There are two type of model in, yeah. If you are if we'll talk about that, then from underground exploration to final production, you are saying, right, of that particular area. So that used to be within 3 months for underground exploration. I'm talking, yeah. For surface exploration, it is 1 year. Yes, from there are two type of that we can see. From exploration to final production, it is 3 months for underground, for underground exploration. After starting a stope and starting and finish of a stope, that is 45 to 60 days. What we are doing at where, yeah, 2 months, 2 to 3 months. So product in production phase, we can divide our production process into two model. First is short term model and second in long term model. In short term model, whatever production schedule we are doing is for quarterly plan or month plan. So based on short term block model, whatever block model I'm receiving from underground exploration, from short term block model to final monthly schedule, this is the complete process. These are the five things that is the requirement for a short term model: grade, lithology, major structure, RQT, and mineralization. Then drilling and blasting design. So we are using two softwares on drill and blast design. First is Aegis and second is Deswik. In Aegis software, while designing a stope or a drill design, you need four type of file basically. First is mining boundary, second is ore body, third is central line of drill level, fourth is development, whatever development you have executed. These four files you will require while designing in Aegis. And fifth one is structural modeling, whatever data you have got from structural model, that will require in Aegis software. Now, what is the benefit of doing drill design in Testwik? uh, we earlier we used to do in AG software, but now we are moving to Deswik software. What is the benefit is you can design multiple stopes in a project while doing design in Deswik software. So that is, and you can also work 2D and 3D in Deswik software. While doing this AG software, you will do only 3D designs. So you can do both design 2D and 3D in Deswik software. These are some modifying factor on extraction of a particular stove. So if we can see, this is the our planned mine boundary, and this is what the actual broken. So there will be some external and internal dilution also, so that you need to consider while planning the schedule. So external dilution is what? D, the that is indicated in red color, that is the external dilution. So what is the extraction is a plus b plus c divided by a, b, c and e. So a, b, c, whatever I have extracted, that is extraction. Overburden, overbreak, that is d part. With respect to a, b and c, whatever I have planned, what quantity has overbreak, that is overbreak, like external dilution we can see. Broken or tonnage is a plus d, extra broken plus whatever broken whatever I have planned. Then recovery plan, like how much of ore I have recovered and what was the plan, and what is the recoverable ton, recovery we can say. We used to see in, like we have 92% recovery in our stoves. 8% we used to lose in during mucking and during blasting also. These are some production schedules that were developed in EPS, like data mine EPS, uh, like yearly production, monthly, 3 month production, weekly project. In production plant, we have 3, 4 type of schedules. In every week, we used to reschedule our monthly plan. Like whatever delay is there in past 7 days, 10 days, whatever, we used to revise our plan on every weekly basis. Then month plan we have, then 3 month plan we have, then 1 year plan we have. Up to 3 month plan we have device plan, and beyond 3 years, beyond the 3 month plan we have only stove wise, to build confidence in operations. I will just take 2 minutes on our shaft, SKM shaft. We have almost 1052 meter depth SKM shaft that has two compartment. The diameter of shaft is 7.5 meter. We have divided the shaft into two compartment by doing partition. One is for material loading, second is for manpower loading. On material loading, we have capacity of almost 3.75 million ton hosting per annum. Now we are expanding it to 4.1 billion ton per annum. Uh, then speed of cage already it is known, 12 meter per second and 8 meter per second. Then we have a copy winder system for that. We have this you can see, like below 395 area is for production. We have established like 2 or 3 overpasses. Here are some overpasses from this level to this level. Ore will be dumped into overpass. Like we have almost we can say 300 meter length overpass. Ore will be dumped from that overpass. From here, LHDs are being used to dump that ore into crushers. So from overpass crusher to conveyor, we have conveyor in minus 490 mrl. So from conveyor, from here crusher to hopper, ore will go through conveyor, then hopper to surface, it will be hauled to the shaft. So that is one of the deepest shaft in India. Then again on long term model, short term model was developed on geological block model, while long term model will be developed on resource model. These are some long term model what we are proposing. These are some design criteria for that. We have ore density of 3.2 meter, 3.2 ton per cubic meter, while waste density of 2.8. Broken ore density, including swelling factor, we are using 1.84 or 1.74 waste. Then stove designing criteria, as I've told earlier, uh, footwall drive distance from ore body contact is 30 to 50 meter. In uh, one more thing, to drill a 300-meter approx, we can say 250 to 300 meter, we are using raise bore operation, which is also uh, big thing. Like we have almost 12 shafts what we have drilled in last 6 months from raise bore operations. A mine layout that consists of these six things. Then resource planning, whatever I have designed, I have to uh, bring some resources like some machines and all. For resource planning, we are using this time use model. So first is calendar time. What is the calendar time is 1 year time, whatever the 365 days. Then schedule time is extended loads are like public holidays in which mines are closed. So that is schedule time. Then availability time. What is the at what time machine is available among that schedule time is the availability time. Then uh, except like planned breakdown, sorry, unplanned breakdown or planned downs, the time is available time. Then from available time, there will be some utilized time and some will be standby time. So utilized time will be for our mining operation. Then uh, from that utilized time, how much the productive time and what is the operational delay. So final product is just real time from calendar time to real time. This is the uh, this is the most working time what we are getting is ready time. So based on this time uses model, like if I will give an example of jumbo, in jumbo case, like our in business plan, what we used to consider is like 78% available time. On of that 78%, 21% jumbo utilization what we used to consider. So 21% will be utilized time considering 113 meter per machine per month. We are using 113 meter per machine per month. We used to plan in that way in business plan, and we achieving almost 105 meter per month per machine from like Sandvik jumbo and M2Cs and all. This is the LSD productivity curve. Uh, then calculating mine life. So Taylor's formula, we used to uh, we used to calculate our mine life, that is 0.2 multiplied by tonnage to the power 0.25. So based on this, our mine life is almost 13 years, we can say. And almost 21 kt per day production we are doing from an underground mine. So I will just spend 5 minutes on this slide. So we are the most digitalized mines in India, we can say. So our digitalization can be divided into these four pillars. First is real time monitoring. Second, predictive maintenance. Third one is reliability improvement, and fourth one is advanced automation system. First, real time monitoring. For real time monitoring, which whatever machine running in underground, we have almost 250 machines at a time which are running in underground. So to track this much of fleet, we have to establish one like digitalized system where I can see where is my machine at that time. So for that we are using optimized software. Optimine software used to provide us a 3D model of our mines. You can track real time position of a particular machine from a digitalized mines control room. So that is real time monitoring. Then predictive maintenance. We have installed multiple sensors in our machines, like in LPDT, in LSD, for solos also, for jumbos also. So uh, that sensors used to capture the data, real time data, like for example, like fuel oil, coolant temperature, whatever. So those data will be collected by a maintenance team in every shift end. Based on that data, only the maintenance will be planned for next shift. So that 1 and 1.5 hour between shift changeover time, it is very difficult for maintenance team to find out the problem. So that is helping us to identify the problem quickly and to resolve it quickly. That is predictive maintenance. Reliability improvement, that is also like tele-remote system, as sir have already explained. In between shift change over time, we use our machines from surface. We can run almost 3 to 4 solos in a shift. So that has almost uh, considering 45 meter per hour productivity, almost 100 meter they can drill in 2 hours per solo. Teleremote operation for great recovery optimization for RFID for RFID network. What I will explain is for diesel capturing. We have installed RFIDs in every machine and diesel pump station, that nozzle. So whenever machine will go to diesel pump station, though those two RFID will be in contact, then only you can fill the diesel in that particular machine. You cannot fill any manual diesel in any machine. Advanced automation system, then belt watch digitalization, digitalized DSR we are using. Optimized software also provides us digital DSR. Whatever the work has been done in last shift, you can extract that information on one click from that optimized software. Thank you. Yes, sir. You're right, sir. It was if I will talk about last 5 year, like before 2017, there was no digitalization. So impact is, as I have told, tele-remote operation. Uh, in a shift, a solo can perform at stretch mark like 5 to 5.5 hours maximum. But after introducing digitalization, you can drill in rest. Right. uh, Earlier, what we are using 5 to 5.5 hours of working hour for a solo, I'm talking now. Using tele-remote operation, I can use that 2.5 hours also, what I was losing in shift change over time. So that is directly additional to our productivity. Like for a one solo, we can drill up to 120 meter extra in a shift using digital process. Second is diesel, as I have explained. uh, Earlier, what was happening, uh, almost 10 to 15% of our diesel used to waste. Like people used to uh, transfer diesel from one vehicle to second another vehicle in underground. So that is being captured by RFID now. So that is improvement of 10 to 15% numbers. Yeah, productivity parts also. Yes. You can we can take actions on operators also based on that data. Availability improvement is there. 72% was the availability in 2016. Now of LPDT we are considering 79%. So on that part it is improvement. Thank you.
So, so like in leapfrog, like one in leapfrog and data mine, one master file is there. So every time you do not require to like upload a data. We just had it is automation. One what we can macro file is there. So we just have to run the macro file and the all data it will automatically select the data with the help of that macro. Means no need to rerun all things. If we run a model and we have need to add more data, when macro file is there, it will automatically search the data and it will clear the data in that file itself. Sub level stop caving not there. Sub level stopping, yes sir. Ah. Yes, actually for the stop purpose, we have one fixed pattern of that holes. So we having like 16 holes pattern is there. So first we are making a raise with help of that stop itself. And like one slice of raise we taking and then stripping along the bore holes. Like no separate raise is not there for the stopping purpose, but raises, main passes, that's are there, but is not for the stopping purpose. For the stopping, raise is making with the help of. Yes, sir. No, no. Actually, stop for like stop. We, we have one stop is like this. Like one stop is like this hole. One entry is above, one entry is below. So and that gate is like a barricade. We have to prepare the gate, and we fill from the upper level, and it is filling goes go up like.
I can understand in cut and fill
Yes,
mining you have very
sledges
specified
for
what
main person entry, not required. Yeah, we having like sir saying we have separate football drive for every stop. We have one separate drive. Like you can see, edges is somewhere like you can see two edges here. Yes, for the ventilation purpose. And we have a football drive here, and this is a stop. The green one and the magenta one. These are the stop. Every stop different uh, separate entries there, separate return is there. Like every stop have different returns. Like we are working at a certain depth, and we have to make our football drive safe. So we are keeping very far this football drive, 45-meter away from the main ore body. 6 meters, sir. Yes, sir. Yes, for every like there is a restriction. Like we have shown you vent seam. It is not like possible to calculate by some person individual. Zero cube. Like every level we have restriction. We can deploy only 3 loader or 2 LHD. It is like it. Yes, it is like that. No, no. In this plan, not only two ridges here, like this is like intake ridges, but in the extremities, we have the exhaust ridges is there. So intake will come from here and going to the extremities and going up to the surface.
We used to have ridges like ridges in football drive. From football drive, we used to make some ducting arrangements, and auxiliary fans used to be there.
What I would like to say is, MOIL will be moving towards to some of the mines in the near future. Will be moving towards to this kind of mining methods instead of cut and fill. So if you have any queries, you can contact them. You can take their contacts also, and whatever issues are there, you can deal with. So yesterday also we spoke about plastic, ring blasting. So here the stoping will require ring blasting, not like what we are doing right now. Stripping. Right now we are doing stripping. Instead, what we will be doing will be ring blasting. So there will be a slot place, slot opening, and then rings will be blasted. Can you show the yeah, this is how the rings will be. So yesterday there was a lecture on that. So all these details, I think that we will make it available. Please, can take request take after the presentation and PDF format वो इन लोगों को दे दीजिए recording. So it will be made available to all of us. So many में details नहीं है. It is just an abstract. Name to main validation. It is only abstract will be available, but the details of presentation you can keep in your database over
स्पेसिफिकली एजिस में बोलेंगे एजिस में हम लोग चार टाइप की फाइल यूज करते हैं सर फर्स्ट इज माइंड बाउंड्री सेकंड इज ओओडी थर्ड इज डेवलपमेंट ड्राइव फोर्थ वन इज सेंटर लाइन रेफरेंस लाइन व्हाटएवर यू यूज yeah drilling level from where either in upload or in download from drilling level वो इमेजिनरी लाइन रहेगा क्या सर क्योंकि आप और नहीं सर उसमें सर्वे का डेटा आता है सर सेंट्रल लाइन सर्वे एक सेंट्रल लाइन लेके आता है हमेशा डेटा उसी से वो लाइन बोल रहे हैं ना सर लाइक डिजाइन लाइन की बात करेंगे तो वो एक स्ट्रेट लाइन होगा सर बट देयर विल बी सम लाइक डेविएशन कुछ ओवरब्रेक भी होगा कुछ अंडरब्रेक भी होगा उसी के पैटर्न में फिर इनको डिजाइन किया
Okay, any more questions? Okay, then we will move on. So please request Pradeep Kumar and I would like to call upon Director Finance MOIL, Mr. Kumane, to felicitate all the speakers for this Thursday. Thank you, sir, for facilitating them. Now we move on. Actually, not to avoid much waste of time, we decided we'll serve tea here itself, so that we don't have to go outside. So now we have our next speaker. I would like to invite Mr. Nagesh Shenoy. He is Executive Director and Unit Head of Malanjkan Copper Project of Hindustan Copper Limited. Please come, sir. So I will read his brief biodata. Mr. Nagesh Shenoy, after completing his BE mining from Bangalore University, joined K3 Copper Complex of Hindustan Copper Limited as GED and was posted at Kolihan Copper Mines. He has obtained the first class mine manager certificate of competency in unreserved and unrestricted category and conducted by DGMS in the year 1998. He has vast experience of more than 33 years in both open cast as well as underground methods of mining in both public sector as well as private sector mines. He is a lifetime member of the Mining Engineers Association of India and has served as secretary of the Bellary Hospital chapter of MEAI for more than 4 years, during which period he has organized several technical seminars and an international seminar. He has also obtained a master's in finance MBA from Sikkim Manipal University in the year 2009. Presently, he is working as executive director and unit head of Malanjkan Copper Project, Hindustan Copper Limited. So he is now from Rajasthan. We are coming to much closer here. So here also they have a success story to tell. So Mr. Shanoy is the unit head of Malanjkan Copper Project, and he will be presenting the blast hole stoping design they have done there and the success they have obtained when they moved from open pit to underground. So over to you, sir. Thank you.
Thank you very much, sir, for your introduction. Good morning or good afternoon, everybody. It's nice to see, even on the second day, such a nice crowd here. Everybody interested and asking good questions also. Whatever I'm going to present today is not any research paper or something like that. It's a case study of what we have actually done at Malanjkhand Copper Mine. A story of a unique mine. Why do I say unique? Because this is the mine which is a flagship mine of Hindustan Copper Limited, which contributes to 70% of the revenue of the company. It is a mine which was initially an open cast mine. We have transitioned to underground mines seamlessly. By the word seamlessly, what I mean is we have done conversion from open cast to underground without any break of production at any cost. And over and above that, we have even achieved a record production since the inception of this mine. So this is a success story of this unique mine, which I'm going to present to you. This mine has got a very long story. More than 100 years before this lease was granted to Hindustan Copper Limited. During the British time itself, from 1872 onwards, work has been going on in this area. Several agencies have worked here. Several personalities have worked here. Several departments have worked here until the DMG of Madhya Pradesh has worked. And then finally, in 1973, this lease was granted. Hello. This lease was granted. Am I audible? Yeah. This lease was granted to Hindustan Copper Limited. Until then, a lot of work has been done on this mine, on this geology of the mine. Even after that also, a lot of drilling and all that has been done. This is the initial stage. The total acquired area of this project is 2016 hectares, and the mining lease is 479.9 hectares. This mine was originally designed by RTZC, and it was planned to produce around 58 million tons of ore at the rate of 2 million tons per annum with a life of 32 years, including the pre-production period. Along with that, a concentrator plant also was planned of matching capacity, and the mine and the concentrator plant started production in the year 1982. It was inaugurated by the then Prime Minister of India, Srimati Indira Gandhi. And as of 1st of April 2024, we have produced nearly 86 million tons of production, out of which 82 million tons is from open cast. Planned was 58.8 millions. We have produced up to 82 million tons and 4.25 million tons from underground. This is what you're seeing is the original plan, which was designed by RTZC for mining up to 376 MRL from the surface, a depth of 204 meters. And let me tell you, when this mine started, it was conceptualized that it will go underground at a future date. So in 1992 itself, a detailed study was done by Mishi Metal Exploration Corporation, and a detailed report also was submitted. Then what happened? There was a delay in the commencement of the underground mines. So what happened was we had reached the limit of production, but as I said, this is the flagship unit of the company, and 70% of the revenue is generated from here. We could not stop the production from here. If this stops, the company finances are affected. So we had to redesign. So MCP, our internal team, redesigned this mine in the year 2009, and we added 10 million tons of this production to this 58 point. And so we went up to 68 million tons at 1.2% grade. That was again, we increased the depth from 376 to 340. And this was planned that with this, we can at least survive for another 4 to 5 years. Then finally, on 30th of September 2011, the underground expansion plan was approved by the government. However, due to some statutory clearances, delay in statutory clearance, we could not commence the underground mining. A tender was floated, and then LOI is issued in 2011. However, due to the delay in statutory clearances, the underground development could not be commenced. So we had to again go back to the drawing table and find out how we can sustain the production. That is when we roped in Indian Institute of Technology, Kharagpur, and then several designs were made, ultimate pit designs were made, and another 10 million tons was added with the plan to at least continue mining from and do the production from open cast till the time underground development and production is started. These are some of the pictures of the open cast mine, how it was in 82, then 2007, and the present pit. Now coming to some important milestones of MCP as we go from open cast to underground. In 82, ore production started. In 92, hydraulic excavators shovels were introduced. In 2009, 100-ton dumpers were introduced. In 2015, the development of the underground mine started. And then in 2022, the production from underground started. So after the statutory clearances were obtained, the contract for the underground development was awarded on 9th of April 2015, an EPC contract, which included a lot of infrastructure development, including the declines, the shafts, the level development, ore passes, crusher chambers, and all the other infrastructures. The main infrastructure included a service shaft, which was 665 meters of depth, production of 6.5 meters dia, a production shaft of 695 meters depth, and dia of 7 meters, and then the ventilation shafts at the two extremes of the ore body, and then declines. Decline of 1 in 7 gradient of dimension 5.5 by 5 meters. Decline is presently used for hauling of the ore from the mines to the surface because our shaft is not yet equipped. We are in the process of like tendering for winder. It's already tendered, winder and shaft equipping and all that. So as of now, we are doing our production from the declines itself. So what I want to show here is a surpack image of the entire mine. We have got the open cast mine, and below this, whatever development we have done as of now, the stopes which we have extracted, and the decline development of north and south. And these are the two ventilation shaft. This is the service shaft. This is the production shaft. All the four shafts have been sunk and lined. We are we are waiting for the tender to be opened, and the work for this equipping of these two shafts and the installation of winder is going to take place very soon. So what in the opencast era we used to use the AutoCAD software for planning. Now we have introduced Surpack for underground, and all the planning right now is done through Surpack. This is the LV section of the entire mine. What you see here is the outline of the open cast mine. This is the bottom of the open cast mine, 340 MRL. Below this, we have left a crown of 40 meters. And then after that, there are levels which are opened here. Yeah, this is the first level, 296, just below this crown pillar. And the level difference of the first and the second level is 60 meters. Subsequent levels, it is 75 meters. The entire design of this is done by IIT Kharagpur. Now, as I said, there are ore passes, waste passes. It is planned to install crushers over here. There will be 3 crushers at the bottom, each of 770 tons per hour capacity. And this is the production shaft and service shaft. Service shaft will have cage, a double deck cage of 100 men capacity. And the production shaft will have 4 skips. And the hoisting capacity of the production shaft will be 1540 tons per hour. These are the 2 ventilation shafts, which are at the extreme, and we'll be having the ventilation fans over here. As of now, these declines have been developed. The north decline like grinding and supplying it in bulk.
So actually, one point is that when you design a base plant, you have to decide what is the source of the material and the raw material. So
Yeah, in the calculations for the finances of this folder had taken, we had considered BSP itself.
okay, we
We had considered BSP, transport from BSP to our unit and all that. On that basis only we have done.
Hey, sir, the question is, sir, after how many days later we are excluding the secondary store? Like how much clean time we are giving for like one?
Because we have not reached that stage. We are filling the primary store.
Okay.
We have taken secondary store where the ground clear is more than 60 or 100 meters.
Because,
Yeah, I would like to say in North Mine they have very good RMRs, 70 to 80, and not many difficulties are faced, and that's why they have gone for PSPS in one of the section there.
Where the ground is
60,
60, 70, 80
Ground
meters.
is more than that.
But what he is asking is different. Paste fill का strength
strength पूछ रहा हूँ मैं.
But the strength of the paste fill.
1 MPa. 1 MPa. 1 MPa is 1 OPC and 9% GGBS. GGBS have high calcium content.
only 1% of
Ozonic activity is high. Hydration index is low.
And
For the plug,
that
it will be
9%
increased.
is slow.
For the plug, it is around
No,
3 or 4%.
the minus 20 microns is supplied by OPC. That is the only thing. Coarser particle is getting from GGBS. That is why they are using 1%.
Actually, it's a binder only to
Just to
reduce
find the minus 20 microns, they are using.
tailings. Only to reduce the fineness of the tailings. You can use cement itself. You don't have blast furnace like you can use the cement itself. It may increase the cost.
No, it will increase the cost.
It may, because no, nowadays what we are getting is almost equal.
You say 43 grade means if you are getting a long-term MOU with, yeah, then I think the cost.
That can, and if you have a plant, in-house plant, definitely.
Yeah, then it's
Thank you.
for ventilation. We have two ranges of boundary.
Yeah. For ventilation, we are having two ventilation shafts at the extremes, and then that is 6 meters. Yeah, and then the declines, as of now, the declines act as the intake, and the shafts act as the exhaust. But our main fans will be coming in another 6 to 8 months. Fans will be installed at both the ventilation shaft. Then what will happen is even the service shaft and production shaft with the declines will become the intake. And we have engaged Professor DC Panigrahi for the ventilation design. So after his study, now what has happened is he has recommended two more raises, one for two more raises, four raises, two for intake, two for exhaust. So that will be maybe another 2-3 years once we go still deeper. Now we are mining from the first level. The second level we are doing the production between first and second level, and we are doing the development over here, and we have gone to the drill level of the bottom one, and then this has gone, I told you, south has gone about 1.6 kilometers, north has gone 2.5 kilometers. So we have yet to reach the bottom. So till then we'll have to install our fans.
Right now they are operating the first level, and their cooling system has just started now. So right now they are doing with lot of precautions.
Yeah.
60 meters
Yeah.
they are leaving and mining. But in the subsequent level there will be lot of
Changes.
Stoping parameters will require lot of changes, because when you have a full-fledged cooling system, then your lots of options will come. So their target is 5 million per annum.
Yeah.
Then I think
We are confident that by 28-29 we'll be achieving our 5 million ton target as what we have planned.
So it's an interesting mine. I think I personally would suggest that those who are working in MOIL, those are delegates here and senior management, they should visit this mine. At least in batches we should visit. And there's one more mine I will definitely would like you to visit is the Rajpura Darika mine. Because they have very difficult rock mass conditions there. In their north load, in fact, you can even push your hand through their rock. Still there, they are doing mining. They are sloping, they are doing sub-level sloping, blast load sloping, all they are doing there with the help of shortcutting and split sets and wire machine. They are supporting the roadways, and now they are doing the mining. I very much recommend you should visit Rajpura Darika mine. And that's a very treacherous mine. So you should see that. and already some officials have visited Imphal, Mahagiri mine. That is also highly fractured rock, highly jointed fractured rock, very similar to your manganese mine. It's a small mine.
And they are using hydrophil.
They are using hydrophil with sand because they don't have mill tailings available there. With the river sand and the cement, they are doing it. So, and there also they have a stove height of almost 50 meters, 60 meters, and the stove wall stands very much stable for several months together because their mining is a little bit slow. They have restrictions in production. They cannot increase because they have planned as a capacity. So, they have restriction in sale also, but I think now it's a little bit relaxed now. But their plant capacity is now the major bottleneck. So they are doing very slow mining, and this wall is standing for many months or even years together. So you can visit these mines and learn from them because we need changes now. we can see that some changes has to be done. So for that, this knowledge, this experience, will always help. I'm really thankful to Dr. Senoy for coming here and delivering his experience of the Malask and Copper project. So I would like
Just 2 minutes. Yeah. For hydrophiling was tried, study was done on that also, but for this method of mining, where we have to, where there's no pillar left, paste is the only option because it has to stand that length also. We can't give any more in situ. So this was the method which was recommended. And as John sir said, I personally invite everyone to come and visit our mine. It's a lifetime experience for everybody. Please do visit her. And this success story wouldn't have been possible without a good team and the support of institutions like Simfer, NIRM, IIT Kharagpur. Thank you very much, Simfer, also for giving me this opportunity to present here. Thank you.
I would like to request Karia Saab to felicitate him.
Excuse me, sir.
Thank you, sir, for helping us with the felicitation. And thank you, sir, for your very good lecture. So, now moving on, we have time, still 1 hour time left for lunch. So, I would like to invite my colleague, Sri Prashant. He is a senior principal scientist at CSIR Simfer. He will be deliver.
Hello. 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 While this is taking place, I would like at the outset I would like to thank the organizer of this workshop to. It's okay. नहीं, वो लगता है। नहीं, they are doing it.
Yeah, meanwhile, I will read his biodata, brief biodata. So, Prashant, he obtained BTech in mining in 1996 and MTech in open cast mining from Indian School of Mines, Dhanbad in 2000. Sri Prashant joined mine backfilling department of CSR Silver as scientist in December 2001 and is presently working in the same department as senior principal scientist. He has completed about 130 R&D and consultancy projects. He has 29 research publications to his credit. He is extensively engaged in the area of underground mine backfilling, paste backfilling, rock mechanics instrumentation for strata control, environment friendly disposal of industrial waste such as coal ash, slag, etc. in underground and in surface mines, and computer aided designing. He has received national award for fly ash utilization by Ministry of Power, Ministry of Environment and Forest, and Department of Science and Technology for R&D on the use of fly ash for stowing in underground mines. So,
प्रेजेंटर भी चाहिए।
Hello, very good afternoon to all of you. And at the outset, I would like to thank the organizer of this workshop for inviting me to give a talk on mine backfilling and in underground metal mines. So I'm just skipping to the main topic. And so as part of my presentation was made by Pradeep in the initial stages, so so it will be like helpful for me for the explaining the second part. So actually, my presentation will be divided into three parts. First, I will be focusing on different types of backfilling, which is the practice in underground metal mines. And then I will be focusing on the two types of backfill, that is the paste fill and the hydrofill. And then I will be going towards the different kinds of studies which have been carried out in our laboratory to characterize the material for backfilling purposes. So this is the brief layout of my presentation. So going in the first part, what is a backfill? So as told already, anything which if you take out a material from underground, it has to be backfilled. So that is the basic definition of backfilling. It can be a one material or a mixture of materials, different materials. So the and depending upon its function, the backfill is divided into basically two types. One is bulk backfilling and another is exposable backfilling. So bulk backfilling is mostly uncemented backfilling, and the main function of this bulk backfilling is to for waste disposal, number one, to provide confinement for ground control and to prevent subsidence and to prevent wall closure. It doesn't have any cement on it. So it is not an engineering product. It can't be changed. It can't be designed. It is just like a bulk filling and just for ground control. The second part, that is the interesting part, is the exposable backfill. Under this, all the cemented backfill comes under this category. So it consists of cemented materials that are placed into stopes where the fill possesses sufficient strength. Why we need a sufficient strength? So as many of the speakers have told that when the primary stopes is excavated, then secondary stopes will be excavated. Then it has to have a self-standing height. It has to have self-strength. So what are the strength? It should be having some cohesion value. It should have some uniaxial strength value. Young's modulus and Poisson's ratio is one of the important parameters that has to be considered. So these factors are the prime importance when it comes for cemented backfilling. Uh, Usually, way back in 1950s, before that, filling was usually done simply by adding fill material to water, and it was hydraulically slowed or maybe pneumatically stored or through conveyor belts. But since 1950s, all the paste fill, rock fill, sand fill, and aggregate fill was added. Cement was added in its prefix, so it all became cemented backfill, cemented aggregate fill, cemented paste fill. It was categorized like that. So moving to the next slide. So these are the few famous methods, like which is prevalent in India, which uses backfilling in conjunction with stoping method with conjunction with backfilling. So overhand cut and fill, underhand cut and fill, it is well explained. They are some of the SK mines and Rajpura mines is using it. And then comes the delayed backfilling methods with sub-level open stopes, shrinkage stope, and room filler. Sub-level open stopes have different variation in India. Like some of using blast hole stopes, some are using VCR methods, vertical crater retreat mining, and all that. So as you must be knowing everything, so like first they do that primary, secondary, primary, secondary. This is the usual scheme for backfilling with cemented backfilling. It's like primary stopes are excavated, then secondary stopes are left, then the third, like 1, 3, 5. One is the primary slopes, then 3, then 5. These are attacked first, and then subsequently 2, 4, and 6 are taken. This is a sequence of extraction. By now, it is well known. If you have any questions, you can ask me now. Because after the primary slopes is excavated, it should have strength to self-stand. That is the main. It has to have a strength to withstand the exposable height of the stope. So this is the major system of mining which is used in conjunction with backfilling. So now coming to different types of backfilling. Uh, I think this has become Chinese, I don't know how, but it was gravity and it was pumping. This is pumping. I don't know, it's like some error is there. So there are like human body, there are three parts of a backfilling system. One is the heart that pumps. So heart is represented by the mixing plant where all the ingredients of a mix is prepared. So ingredients, what are the ingredients? Ingredients is water, ingredients are tailings, ingredient will be sand, ingredient will be OPC, ingredient will be replacement of OPC like slag or maybe fly ash. So these are the ingredients which are the main, which are used to form the fill material. And then the distribution comes. So distribution comes with like, we have to find what is the horizontal extent where it is to be distributed. What is the head available? So if suppose the depth of the mine is good enough, then the gravitational head is enough for transporting the fill material. So depending upon that, we decide what kind of transportation system we need. Either through gravity itself or we need a pump, because if the horizontal distance is like 2 kilometers, like or maybe 3 kilometers, and if the vertical distance is like 1 kilometer, so it won't, the gravitational head won't be sufficient to push that fill material to the extreme end. So there comes the difference in the head and the extreme end is provided by the pumping system. So we actually do the hydraulic profile and hydraulic gradient. You must be knowing of that. Do you have idea of hydraulic profile or hydraulic gradient? So hydraulic profile and gradient is like that. From the what is the head we are getting to the extreme distance, we draw a straight line. That is the head available, and the profile is the profile of the pipeline. The pipeline profile should not get the hydraulic head, because if it cuts the hydraulic head, there will be stagnation. The flow will be it will be blocking the flow. So that is the design criteria. Then the after it is placed to the stopes, what we do the dewatering, densification, and monitoring part. The monitoring part usually consisting of monitoring of the both paste plant as well as the monitoring of the at the barricades and the stopes itself. So, uh, this is a brief schematic description of different types of backfill thing. So this is the rock fill, this is the hydrofill, and this is the paste fill. As you can see, as you are seeing that in hydraulic fill, in cemented hydraulic fill, we need a complicated barricade system and a good drainage system, because the ratio of water is like we put generally 70 to 75% solid and remaining 30 is water. So we need an elaborate drainage system for hydrophils. That is not the case in paste fill. In paste fill, the barricading system is kind of simpler, because the load coming on the barricades are less, because the hydrostatic pressure buildup is less, and most of the water which is sent in paste form, like 85% concentration is solid. So it, as told by Pradeep, it is used for hydration work, like cement hydration. Calcium oxide to calcium hydroxide has been formed as a cementing material. So there is no need for any hi-fi drainage system. And then comes the rock fill. So what is rock fill? Rock fill is what we get from the mines when we drive or like a cross cut, or when we have a drive edge. The material which is produced from the mine itself is used as a filling material. So here we see the development is going on, and it is going to the LVDTs, and it is directly going to the underground mines. So and it is not like that. Rock fills can be used both in primary stopes as well as in secondary stopes. And in primary stopes, they usually mix the rock fill with hydrofill. So hydrofill is what? Hydrofill is mixture of tailings and cement. It forms the matrix. Okay, it forms the matrix within which the rock fills are placed. So we need a suppose in the primary stopes, what is done, like rock fill is placed before and then hydrofill is placed. Cemented hydrofill is placed. The main purpose of cemented hydrofill is to form the matrix. And in certain cases, what happens that initially the hydrofill is placed and then the rock fill is placed to form a mesh, like a matrix form, to have adherence between different boulder size of the rock fill. So usually the ratio of hydrofill to rock fill depends upon the kind of strength you need. So that is the main governing factor in the ratio of mixing of rock fill and hydrofill. So this is the, and usually what the mine people do is that in primary stope, usually they use hydrofill, cemented hydrofill and rockfill mixture. And in the secondary stope, they usually just fill the secondary stope with rockfill without any adding cement to it. It will reduce the overall cost, because secondary stope doesn't require a free face, because it is already filled with, which like adjacent side will fill with cemented fill. So that is not the important thing to do. So when we come to hydrophils, the main factor is which has to be taken care of is to and underground is to form the barricades. Okay. So in bulkhead generation, two things is to be done. One is the bulk. One we have to found out the plug, and then we have to design the barricades. So during plug filling, it is not that instantaneously the plug is filled up to 7 meters height. It is done in casual cycles. Why it is done in cycles? Because if you put instantaneously 7 meters of this thing bulk plugs filling, then the pressure at the barricades will be very high. So what we do it fill in cycles. Suppose the design parameters of a barricade is 250 kilopascal, and what we do, as told by Pradeep, we have contact pressure cells over here. We monitor the filling, monitor the pressure which is coming on the pressure cells, and what we during the filling and post filling also. So if the design strength is like 290 kilopascal, and if the strength, if the reading is like 200 pascal for during filling, then the filling is stopped, and when the pressure reduces to another like 150 kilopascal, then again the pressure, this stope, bulk filling is done. Like stope, this thing is done. So that has to be taken into account while forming the plug. So plug is usually having more cement because when it solidifies, it takes all the load from the bulk fill. So this is very important because it takes the load on the barricade coming after the filling of plug is less when you compare to plug fill. So that is the thing. So in plug fill also here there are decantation towers, decantation pipes, corrugated pipes having perforation on it, and it should be laid before the sewing operation start. The pipeline should be laid from the top level to the decantation level, and there are different perforated pipelines also, which dissipates the water during the plug formation. So there is a combination. But in case of paste fill, that is not the requirement because the water is very less. So these are the decantation pipes, as you can see. This is the rock fill, and this is the aggregate fill. And in filling, the most important factors which we consider is the size. The size does matter in case of backfill material. So this is the thing. Next slide. So what are the different criteria, difference between high density fill, low density fill, paste fill, and rock fill? This is the usually the placement state is like 60 to 50 to 60% solid by weight is low, is used for low density fill, is classified for low density fill. 60 to actually it is 75. 75 is for high density fills. 75 to 85 is for paste fill. That is the solid concentration. And in rock fill it is dry. So underground transportation is either through borehole or via pipeline or through gravity. For high density fill, it will be cemented, and for low density fill, it is uncemented mostly. Paste fill, it is like through borehole via pipeline through gravity, or it can be pumped also, depending upon the horizontal distance it has to travel. Then rock fill is done by raise, winch, or mobile equipment, LBDTs or conveyors to use for transporting the waste material to the voids. So binder application is, as they are told, it is uncemented for low density, high density cemented, as well as uncemented, depending upon the end use. Then the cemented only is, sorry, paste fill is cement only, OPC grade 43 grade, is used. And pozzolans, why we use pozzolans? Cement actually contributes 75% of the total cost of backfilling. So mine management usually try to replace with the binder alternative like pozzolans. What are pozzolans? Pozzolans are siliceous or aluminum siliceous material having free lime. When it contact with water, it produces cementous properties to increase the overall strength. So usually all the mine management are replacing sand with some extent with pozzolan material. And rock fill, as told, it is uncemented, but it is used in combination with cemented hydrofill. So water to ratio, water to cement ratio, water to cement ratio is an important factor which we have to consider with respect to the strength development. Suppose if the higher water to cement ratio, the lower is the strength, so, and vice versa. Paste fill have got low water to cement ratio, so that is why the strength development by paste fill is very high. And similarly is the, suppose cemented fill is either is rock fill is either 1:1 hydrofill and cemented hydrofill and 1 rock fill in the ratio 1:1 or 3:1 depending upon the strength requirement combination. The placement rate is like lowest for low density fill because the density is less, suppose 50% solid by weight, so therefore the filling rate is also less. Similarly, it goes to 100 to 150 for high density fills. Usually it is a general average filling rate. And for paste fill, it might go to 50 to 200 depending upon the what is the requirement. So this is now it has been increased to more than 200 recently. It's like with improved pumping capacities. And for rock fill, it is 100 to 400. And now it comes to segregation. What is segregation? So if the water is high, what happens that the finer particles, it moves to a different larger distance because it is the water content is high. In case of low density fills, what happens when you put the pore into the voids, the cement being lighter flows away from the point of pore. So if you take out the pores from the backfilled area, we won't get even strength. It will be the strength is not even because of the cement segregation. Here in case of hydrofill, that is the maximum thing. But in case of paste fill, that is not an issue because the solid content is high, and the paste, the cement is evenly distributed within the fill mass. So it is more reliable. As Pradeep said, it is so reliable that they can drive a haulage road inside. They can drive a working road inside it. And for stock and for rockfill also there is segregation. So why is the segregation in rockfill? So larger size boulders like 13 centimeters, 15 centimeters, they fall in the same range. But the beach formation for smaller particles like aggregate fill kind of thing, they move to a greater distance inside the stove. So the density of packing is very different. So that is the main issue for rockfill. So to eliminate that, they should have different points of pouring to increase the evenness of pores. So that is the thing. Stiffness, low density fills like slurry fills have got low stiffness because of the segregation in cements and all that. And paste fill has got low to high, and rock fill has the maximum stiffness. Grain size, now grain size is like top size is 2 and usually not more than 10%. For why we need, usually hydrophiles usually is having, there is a thumb rule that 10% of the particle should 20% of the micron size should not be more than 10%. Means like the final particle should be restricted. Why it is restricted? To have a percolation rate of 10 centimeter per hour. If the percolation rate is 10 centimeter per hour, then 70% of the water percolates out from the stove. If it is a thumb rule, we found what we do in the laboratory is we do what the constant head permeability test, and we found out what is the percolation rate. If it is more than 10, then we can go for this hydrofill on the basis of the results. And so 15 in paste, we need 15% of the particle must be finer than 20 microns. So when we mix sand or water, and when we pour inside, when we pour the water and water and sand slurry, what we see a segregation, quick segregation. So there is no retention of water in the rocks, in the coarser particles. So what is the difference between paste and the normal fill is that paste is having 15%, what sir has told, that it needs finer particles. Why it needs finer particles? Because it traps water inside the voids. So what is the function of that? So when the water is entrapped into the fine particles, it forms a lubricating material. And the flow inside the pipeline is a plug flow with the finer particles going to the periphery, and the coarser plug being in the center of the flow mass. So it acts as a lubricant. And if it is fine, it will retain the moisture, which is very important for transporting. So that is why fines and total tailings are required. We are not classifying any tailings while using paste fill. So binder quality requires a large number of binder for low density fill because it gets segregated. So we need more cement for that to achieve the same strength. So binder quantity is usually low for paste fill because for lesser cements, as the cement is evenly distributed, we get the same strength. And for rock fill, usually, binder is for moderate binder quantity is used, and basically the binder quantity is provided by the hydrophils. So barricade is very expensive for low density slurry fills and cemented fills, which is inexpensive for paste fill because in paste is a highly viscous material. So we need only muck and a little bit of shotcreting. That is good enough to retain the paste fill. So the cost is less, and moderate binder and rock fill it is not necessary. It's like for barricade because it itself retains the angle of repose of the material, forms the end of it. So water runoff is excess for hydrophils, and there's a lot of pumping costs involved. Water runoff is negligible for paste fill, and no water is runoff is for rock fill. So capital cost, the highest capital cost is for paste fill. Initial capital is like 100 crores. SK mines, they have used like 100 crores, but for hydrofill plants, the capital cost is relatively less, and for rockfill, it is moderate capital cost. Operating cost is lowest for cemented fills like paste fill, and operating cost is very high for hydrofills, and high operating cost is for rock fills also. Just summary between comparison between the paste fill and the hydrofill. So slurry fill is classified as low and to high density solids. Low means like up to 60% solid by weight, and 60 to 70%. It is 75 actually. 75% solid by weight for high density cemented fill. So it is transported in pipelines through high vessel velocity. So there is a formula by Condoleezza and Duran and Condoleezza which founds the critical velocity. What is the critical velocity? Critical flow velocity is that velocity below which the materials start to form a layer inside the pipeline. So the flow is, this is the kind of homogeneous flow when the concentration of the particles are evenly distributed across the cross section. Second one is the heterogeneous flow where the concentration of the particles are on the higher side at the lower end of it. Third is the saltation flow where particles is moving in small jerks, like little bit jerks and all that. But there is no layer formation at the bottom of the pipe. The layer has not of solid particles. And the flotation with stationary bed is that kind of flow where the velocity, critical velocity is the slurry is flowing at just at the limiting critical velocity, and there is a layer formation at the bottom of the pipeline, and the area of cross section is getting reduced because of the layer formation. So what is the ideal thing? The ideal thing is that the material should flow in a heterogeneous manner throughout the having a uniform concentration distribution along the cross section. What is paste fill was first used in grand mines in Germany in 1980s, and it is just like akin to a toothpaste. So what we use in the morning when you go out, when you do like this, the toothpaste it does not fall itself. We need to squeeze it. Okay, that squeezing is called yield stress. I will be coming on that later part. So before the yield stress, before the paste attains the yield stress, it remains inside the Colgate, inside the tube. So that is the thing we need to have a minimum stress which requires the paste to flow. So it is what is a slump test? What a slump test is the test which has been carried out in the lab, which determines the consistency of the fill. It is an inverted cone. I will be explaining in the later slides what is a slump and what how it is test has been will be carried out. And as per Golder Associate, a paste can be defined as a mixture of solid and water that has no bleed, water bleed when kept idle. That is the standard the definition from Golder. So what is the difference between the two methods? Paste fill low permeability with little or no water bleed, hence binder and leachate washout is less reduced. So there is not an issue of leaching because usually the environmental people usually are concerned with leached out water. So in case of paste fill, that is not an issue because water is very less. Reduce mining dewatering cost as water is less. Enhance fillings rate because high concentration. Hence mining cycle time is reduced. We can go because of the enhanced filling rate. Laminar flow in pipelines reduces wear and tear because as I told you earlier, finer particles is in the periphery, so the wear and tear of pipelines is very less. Usually they use seamless pipes for paste fill that is having high endurance for pressure gradients, and prevents loss possible liquefaction. So what is liquefaction? Liquefaction is a phenomena which like when you uh, pour a material slurry, so between the pores there are water inside it, so they exerts a pressure that is called a pore water pressure. So when that solid mass having saturated or partially saturated with water, if it is fully saturated, all the interstitial particle spaces are filled with water. Okay, and when the dynamic loading comes, like cyclic loading is coming, so what happens that at an instance when the resonance is there, so particles is vibrating with the natural frequencies, and when the frequency external frequency like from blasting it comes, so the whole mass becomes fluid because the pore water pressure exceeds it, the limiting the confining pressure, so the whole mass becomes fluid. So that is the main thing, what that is the main danger for low concentration fills. But in case of a paste fill, that is not an issue because whatever water is there, that is for hydration and all that. So prevents possible liquefaction is there. So what are the hurdles for the space plants? So high initial investments. Usually mine management doesn't want to put their money before they get the returns. So that is the main thing. Strict PLC control is required because PLC is very important because a slight change in the moisture content, a slight change in the moisture content of a paste fill produces a huge change in the pressure drop. So that is a very important to be noticed. So they should have a strict control of what are the ingredients getting placed inside the for making a paste. So that is very important. And relatively new technology and many technical aspects are not fully understood. But I think people are learning from their experience as of now. Like, and so slurry fill is relatively simple, small infrastructure, less operating cost, requires minimum technical supervision, lower capital and operating cost, and all that. This is simple for hydraulic fill. So what are the hurdles? Excessive water needs to be recovered and pumped, so pumping cost increases and all that. Reduced fill strength due to cement water segregation, already explained. So increased because these some of the slimes which get through the decantation pipe, it has to be pumped out, so the cost increases in that respect. Uh, Bulkhead dewatering facilities construction and curing process interrupt the mining because of the low cycle, higher cycle time of the hydrofill. The mining cycle increases and the production, there is a loss in production. That is the thing. Now I will just touch out the design factor. What are the designing parameters which are taken into for account for designing a slurry fill plant as and designing the paste fill plant? So first we will look out the mining environment and geological condition at the site. Okay. So what are the mining environment? Mining environment is rock condition, including the hanging and footwall, the host rock and the country rock, and the ore. Mine operation period. At what time will be the stope will be exposed, and mining method and its classification. What kind of mining method is going to be installed for that particular kind of scenario of country rock, and mining geometry, that is the height, the length, width of the mining object. What are the primary stresses, which is involved in the this water principal stresses, major and minor, that has to be taken into account. Then the geological condition, like whether there is faulting, whether there is dike, this has to be considered while designing in the designing parts itself. Then what is the purpose of the backfilling? Depending upon the mining method, whether what kind of backfill we are going to put, whether we need cement in it, whether we are used for waste disposal, depending upon that we'll decide. Okay. Now when that is decided, then the material characterization is done in lab. What are the things which we do in the material characterization? First we carry out the physical characterization. In physical characterization we find the pulp this thing, dense specific gravity, bulk density, then percolation rate, then this thing void ratio, porosity. All these are the physical parameters which have to be tested before classifying a material for hydrofill. For paste fill also we do the same thing, but in that case size is the most important things, and the strength what it gains, and at what percentage of cement. That parameters we play with to find out the ultimate target strength of the stopes. So this has to be done before, and then define define operation parameters so that the material backfill matches the target properties. Then after the target properties has been defined, suppose we need 1 MPa strength, okay, for a particular fill. So after that is defined, then at the fill plant, the operator should mix the same ingredients. Suppose 1 MPa we are getting for cement of 5%. Just imagine, just an instant. So the operator parameters should, and with a pulp density of like 1.5. So the pulp density has to be with what are the variables? The pulp density, the solid concentration, the velocity, and all that. So it has to be synchronized in such a way that we get a mix which is which is favoring our fill plant. After that, what we do the economic evaluation. Suppose what is the binder cost coming, how it can be replaced with a different material. After that, then documentation of mine back filling system. What are the things which has to be done? How many hours it has worked? What is the filling ratio? What how many cubic meter of the this thing fill has been poured inside this wort? This has to be taken into account and put into a record book, online record book. So to keep they keep a record for that. So what is so backfilling purpose? It may be pillar recovery. That is a simple. It's like what here that it is explained over here. Sill pillar recovery, working platform, ground support, waste disposal, mining on top of or sides or under the backfill. That is the things which are the parameters which has to be taken into account. So backfill placement operation includes dewater placement and monitoring. The monitoring part is to be done for both the paste plant for the plant as well as for the underground. So what are the monitorings which have to be done? We have to monitor the pressure which is coming on the barricades. We have to monitor the velocity, and then we have to monitor the density. So there will be a instrumentation at the paste plant also. What kind of instrumentation is that? Density meter is there, then velocity meter is there, then at the barricade pressure cells is there, and if it is hydrophile, piezometer should be installed to find out the variation in the pore water pressure. So this is the main basic outline of a paste fill hydrofill plant. So the material from the mill comes to the hydrocyclones. Hydrocyclones is basically uses centrifugal force, principle of centrifugal force, which to reduce the to size, basically classify the tailings into coarser and finer particles. So the top particles, the particles coming out from the top of the hydrocyclone is sent to the ash tailing ponds, and the coarser particle which is required for hydrofill is taken into consideration for backfilling purpose. It is diverted to the backfilling plant. So it will then it is going to the settled storage plant. There is a mixing plant. There is a cement silo, and in one the cement silo will be replaced by partially with an ash or a GGBS silo to replace the cement. And there is a water, then there is a continuous mixing, and it goes to the underground. So hydrocycloning can be done in if you want strict control, then we can have two circuit of a hydrocyclone if we got strict control of the particle size. Otherwise we can go for one this hydrocyclone also. uh, Classified, so what is the requirement? Classified tailings not less than 20% of the particles less than 10 microns to achieve a percolation rate of 10 centimeter per hour. So this is considered, this is determined in our laboratory. So if you get a percolation rate of 10 centimeter per hour, it means that water 70% of the water is percolated out from the stove after 124 hours. That is a thumb rule what we have seen in different mines. So tailings are pumped up directly to the mill tailing. That is a simple what I have told. What is the difference between concentration? Fines are rejected as overflow, and coarser particles discharged as underflow with density of 50% by weight. Then underground reticulation at desired concentration. The desired concentration is manipulated by adding more solid and less water to it. So now coming to the paste fill design. So paste fill, basically it is composed of three components: water, tailings, and binder. So tailings are usually more than 75% by weight. Binder is like it varies. Like OPC is 9%. They can replace it by maybe 5% of slag, or maybe 5% of ash, depending upon what gives them the design strength. And So first, the material properties, as I have told you earlier, it will be determined in the laboratory. Then the grain size adjustment will be done, because as sir told by sir itself, they didn't have for paste filling plant, didn't have the finer particles, so they use cement. So that is called the grain size adjustment. So we plot a curve, and then we find out whether that curve is having a minus 20 microns particle size, at least 15%. If we are not having that, we introduce some finer particles to match that grain size. That grain size is called a Fuller curve. We superimpose the what materials what we got from the field, and we superimpose into the Fuller curve, and we matches out. So suppose that it is not matching it, so the final particles are added to it so that it matches the curves. The Fuller curve is that curve that gives you the maximum compaction, maximum interparticle. It's like there is less interstitial space between the particles. So the pressure gradient estimate, this is carried out by closed loop test. They mix up particular mix with a particular pulp density, and they flow it into the pipelines, and they do the pressure. What is the drop in pressure for a particular pipe diameter and for particular velocity? Then on that basis, travel distance estimate is done, and that on that basis, plant is location is decided, whether it is located on the surface or whether it is located in underground. So underground, there are two type of plant: that is fixed plant and mobile plant. In fixed plant, as if the plant is fixed, we need a pump system, and then for surface plants, we need either it can go through gravity or by through pump, and then the same thing follows. So what is a paste, and difference between paste flow and the normal hydraulic flow? A paste flow, as told, is a plug flow. The pumpability of paste depends upon its rheological properties. What is the rheology? Rheology is the deformation of material when subjected to external force. That is what rheology. This, I will explain it on more on while we touch upon the laboratory studies. It does not obey the paste does not obey Newtonian flow. It is follows a non-Newtonian behavior. So what is the difference between Newtonian flow and non-Newtonian flow? In Newtonian flow, the stress is directly proportional to strain. Yani, means when you pull the grass down, the water flows itself. That is a Newtonian flow. There is a straight line between stress and strain. But in case of pump paste flow, we need to have some initial strength, initial stress to make the place flow. So that is not a non. That is not that behavior is a non-Newtonian behavior. So this is the plot of a non-Newtonian flow. So this is the shear rate and this is the shear stress. This is kind of a little bit scientific part. So I'm just telling you in a layman term. What we do, we have a rheometer with us in our lab. Suppose we make a paste of 70% solid by weight, and we do a rheological study. A rheological study mainly relates this shear rate with the shear stress. If we get these two values, then we can find out the yield strength. The yield strength is that this is the yield strength. This is the yield strength. This is the squeeze, what I was talking about. This is a squeeze which you require for making the paste to flow. So with this, this is the generalized rheological model, what we follow. And usually there are two type of models which suits our Indian condition. That is the Bingham plastic model. That is, we know the value of shear stress and we know the value of this viscosity. It's like by knowing the two unknowns, we can find out the yield stress. So for Bingham plastic fluid, relation between the pressure gradient and flow velocity is given by a Buckingham equation. So the pressure gradient, that is very important for this is the pressure gradient what we need to find, and by rheological study we find out the viscosity as well as the yield stress. This is the by this we can find out we can predict the pressure gradient for a particular diameter. Here D is the internal diameter of the tube or the pipeline. V is the average slurry velocity. Length is of the pipeline which we are taking into account. So by this formula, we can predict what is the pressure losses. And on this basis, we can find out what is the distance it can travel for a particular scenario. It's like a full pump, as I told before, full scale pumping loop test on paste of desired consistency is necessary to determine the pressure gradient, head loss of various combination of pipe diameter, flow rate, and throughput. So this is the factors to be. Results of loop test will determine the operating pressure and the choice of pipe and the flow rate. All these factors, all these things, what we are doing will is a designing factor for what kind of pump we need, because piston pumps are used for paste backfilling, reticulation of paste backfilling. So these factors act as an input for determining the paste pump. So Pradeep has already showed this cycle and all that. So the tailings come from the tailing plant and it gets through a deep bone thickener where the concentration is 58 to 62. It goes to the filtration where the filtration disc filters where the solid concentration increases to 83, and then it goes to mixing with cement, OPC, water required to form the required pulp density, and then it is reticulated to the underground through positive displacement pumps. So what are the three essential things? Dewatering, mixing, pumping, and transportation. These are the major components of a paste plant. So there is disc filters what I was talking about. Disc filters works on the principle of alternator suction and blowing part. So paste materials are placed inside here, having a concentration of 60 to 70, and the disc rotates. So when the disc is at the lower portion, like half of the trough is filled, there is a suction. So and when it rotates to 180-degree, there is a blowing part. So during the suction cycle, the final particles sticks to the outer surface of the disc, and while it rotates, when the disc is inflated, the cake gets displaced into the this thing conveyor belts. This is a diagram of a deep cone thickener, and these are the different dewatering techniques which we use. But mostly, we in India use this combination of deep cone thickener and disc filters. This high density thickener, cyclones, centrifuges, tank dewatering, just to mention few of them for dewatering purpose. So mixing is done by two process in a paste plant. That is continuous mixing, and then another one is batch mixing. So continuous mixing plant requires higher maintenance and properly calibration because as I told, a slight difference in the particle size and the moisture content will reduce a great difference in the pressure. So that has to be taken into account. The mixer is screw type mixture, and it cannot respond quickly to incorrect paste means passing to the underground distribution system. Sorry. This is a batch mixture. Batch mixture is self-calibrating. Suppose if a wrong pulp density is formed into the mixture, so the agitator of the mixture is driven by a pump. So the pump, the power consumption of the pump will be changing depending upon the consistency of a paste. So it gives a feedback signal to the water sensor to increase the water quantity so that the pulp density is maintained. That is the case for batch mixing. So it is easy to control, and it can this is the main thing. uh, I don't know. Anyway, so the transportation to the underground is done by three methods basically. One is a gravity system, which is a combination of vertical and horizontal pipelines, where the this thing vertical head is converted into horizontal length in steps. Another one is that pump is installed at the bottom, and the third configuration is that pump is installed at the surface, and the discharge is taking place through a longer horizontal distance, then it going to the vertical downward location. So there is in the first configuration there is a no disruption of surface activities because it is in the inside the mines. And another, the main disadvantage of this kind of configuration is that space constraint is there, so maintenance will be an issue for that. And then in the second configuration, it uses both horizontal and vertical gravity, it's like pressure. And in the third, easy installation, inspection, maintenance with no disruption of main shaft. Disruption due to surface activities will be there, and because if there is something happens to the pump, the whole system will be stopped. Filling up, because filling operation mainly depending upon the pumping of this facility of the pump. Then high pressure takeoff at this point, because there is a vertical head, therefore the high pressure is developed at the bottom of the pipeline. So this is the pump which is used for pumping the paste. That is a double acting piston pump. When one piston moves up and the other piston goes down, so there will be a constant flow. And because of this, there is some pulsation, which is reduced by pulsation dampness, what they use inside what they use in the plant. So the pumps manufacturer are basically Kuzmister, Swinch, Able. These are the few pump manufacturers that are supplying pump for paste plants. Uh, so now I'm coming to the laboratory studies, what we do in our labs and how we classify things. So we get the proper like raw materials from the disk filters for material characterization. Then we get the mill tailings, we dry it and do a coning and quartering, and we get a representative sample for mill tailings. Then we get the different pozzolanic materials like fly ash, then slag. We do the sampling by coring and quartering, and OPC. These things are the parameters on which we do the laboratory studies, and it basically involves first time XRF characterization, that is the chemical composition characterization of a material, different film material. Then we go for particle size analyzer. It is a laser based. We use a Malvern based laser particle size analyzer. Then we mix the paste and prepare the paste of required pulp density, and when we do the slump test to find out the consistency of the, we usually we get the target slump and the target strength from the mine management. So with that particular target strength and target slump, we have to change the this thing cement binder content, so to achieve the target strength. And and the main objective is to our main objective is to replace the binder with OPC binder with different substituting material. So that is the main thing that is to be done. Then we go for after some test, we prepare the molds. Then we go for testing, geotechnical testing. This is the compression testing, and this is the triaxial test. Then the sample is failed, and we get the result. Suppose a target UCS is like 1 MPa. Then we after making the molds, we cure it for different days: 7 days, 14 days, 28 days, and 56 days. This gives the idea at suppose the target strength is 1 MPa, and suppose with a particular mix we are getting the strength in 28 days for a cement percent of 10. Suppose we reduce the cement percent to 8 and we increase the fly ash content in cement. The binder is 10%, Initially, we do a 10% test, that is the control sample. Then we start on reducing the binder content and we add on ash or slag to it, so that we can see what is the effect changes in the strength parameters in different curing periods. After we get that, then we can say to the client that with this binder replacement and with this curing period, we can achieve the target strength with this days, with this many days. And then we can go for microstructural analysis and SEM analysis. So these are the main laboratory studies which we do at SIMFA. Now, physical properties, what we, as I told you, that particle size distribution, we do specific gravity, bulk density, particle morphology. This is done by SEM analysis. Then void ratio and porosity. Relation between slump and water content we find out. Then paste rheology from the rheometer we find out to find out the yield stress. Then if the factor of safety for a particular stope dimension, that is also important. So where we get from, like, how do we get 1 MPa strength is required. So we do some numerical modeling as well as analytical analysis. So with a particular stope dimension, with this, what is the factor of safety of the fill material, we find out in the lab. That is this is how we decide with a given dimension what factor of safety we need to be having a safe fill. So void ratio is the ratio of volume of the void to the volume of the solid. It ranges from 2 point. We have got a mercury intrusion porosimeter with us. It gives us the porosity value as well as the void ratio value. So with that, with the help of this instrument, we found out this parameter. So usually size is important parameters what we have told. So materials are classified as uniformly graded and well graded. So what is a well graded? The difference between well graded and uniformly graded particles. In uniformly graded particles, as you can see, the size distribution is very narrow. Means like it means we have got similar kind of particles of means like suppose we have a glass tube and we put the marbles of same shape, then it means that the void ratio will be high because the particle size are of same size. Therefore, the void ratio and porosity will be high. So next type of gradation is the uniformly graded. Here we get evenly distributed particles. We get smaller particles as well as the larger particles. So the void between the larger particles is filled with the smaller particles. So we get a more compact fill. So that is a very important thing. And this is the main governing factor which changes the kind of fill we are going to adopt, kind of filling system we're going to adopt. So this is done by a laser-based particle size analyzer. This is the some of the results from SK Mines, SK Mine GGBS and SK Tailings. These are the comparison study. So CU is the yardstick to measure the whether it is well graded or not. Q is called the coefficient of uniformity. D10 is the particles diameter at which 10% of the material by weight passes. So D10 is a suppose you are getting this D10. Is what is the value of D10? Anyways, I will just skip it. So this is the same setup we are having at our lab to determine the elemental composition. This is the basic like of this XRF output, and this calcium oxide is it's like different parameters we found out in the lab. What are the chemical composition of a particular tailings or maybe fly ash or maybe GBS or maybe just like mill tailings. So these are the morphological studies output. This is the ash. There is a cyanosphere. This is the morphological study for tailings. So this is the hydration index and lime saturation factor. What we do is for pozzolans, we do the chemical composition analysis, and from the output we do the hydration index study and the lime fraction. So hydration index, if we have a hydration index of 1 or more than 1, it means that it has got reactivity of pozzolans is more. So it will attain more strength because it will having more calcium oxide. So calcium oxide should be more. So we can have a good hydration index. So it should be more than 1. If it is more than 1, it is suitable for as a pozzolan. This is a yardstick, just a yardstick. Same is for lime saturation factor. It is a ratio of calcium oxide, silica, and silicon oxide, and aluminum oxide, and iron oxide. So this is a slump test. What I was talking about, what we do. Slump is the subsidence. Like if we pour, if we mix it with the required pulp density, and we pour it. What is the? This is the subsidence. Usually it varies from 0 to 200 to 300 mm. So we can see the difference. This is a slump of 184 and this is a slump of 94. What is the difference of the subsidence which is taking place? So it usually tells the consistency of a fill, how it will behave when it is poured inside the stove. So when we go on increasing the water content, the slump also goes on increasing because it's the spread will increase because the flowability will increase. It means that the flowability is increased. So these are some of the samples for rheological studies. Rheology is, as I told, study how the study materials behave on response to applied forces, and it establishes a relation between shear stress and the shear rate to determine the yield stress and changes in viscosity. So usually, as I told you earlier, the Bingham model follows it is more for suitable for extrapolating the yield stress. So we use that model, and we can see as we go on increasing the concentration, the yield stress also increases. So that is the thing. So this is the formula which is used for determining the factor of safety. This is an analytical approach given by Michel way back in 1982, and it has been modified by different authors. So the factor of safety is given by different parameters, and if you know the factor of safety, and this formula is a simplified version of this formula. If you know the factor of safety, suppose factor of safety is 1.5, then we can change this parameter into this, and then we can get the value of C, what amount of C we require for a particular width and dimension of the slopes. And similarly, what is the UCS strength what we have to get for a particular width of exposure, height of exposure. So this formula we use for determining the factor of safety of the material for a given slope dimension. And so there is one analytical, sorry. Second one is the numerical modeling approach by which we can find what is the cohesion and the UCS strength required. So this is a flag 3D model, what we usually do. And now we also do carry out studies on paste backfilling performance. So we take out cores from the backfill area portion, and when they subject it to different geotechnical studies. This is the extracted block. We take out coring processes there. Then we take the cores, and then we subject it to uniaxial strength determination, and then the UCL samples are prepared, and then we found out whether strength gain in the underground mines is same as what we get in the laboratory, and what is the discrepancy between the laboratory value as well as the what we are getting in the field. So what we found that usually there is a discrepancy of 10%. 10% less value is there in the field. So this is a kind of rupture what we are getting. This is a shear failure. This is a tensile failure, and this type of failure represents a mixture of combination of both. So I'm trying to hurry up because you must be feeling hungry now by now. so these are the projects which is going on as of now with us. And one is we have done a geotechnical study for Malanchkad also. We are having two projects from SZL for replacement of OPC with GGBS, and scientific study is going on for paste backfill and RDM for top-down methods, and that is it. We are doing some studies for INFA also. So that's it. Sorry for keeping.
Any questions? Anybody? Thank you very much, Mr. Prashant, for his deliberations on backfill mining. So I will request Karya Saab to felicitate him. ओ भाई साहब इसको टेप करने बोलिए लोग गिरेगा हटाना पड़ेगा इधर दीजिए। Thank you very much, sir. Uh, and thank you, Dr. Prashant, for his lecture. नहीं इसको मत हटाओ, इसको जरूरत लेकिन उसको काम नहीं कर पुराना वाला हटा दीजिए और इसको टेप कर दीजिए, टेप करने से बस है। So now we'll break for lunch and we'll assemble here by around 2:30. Okay. Thank you, Karya sir.
निकाल दिए क्या?
ये इसका है पेन ड्राइव निकाल दिया, पेन ड्राइव निकाल दिया। इसमें ऑफ करना पड़ता है तो बैटरी खत्म हो जाएगी।
बढ़िया बनने की कोशिश कर रहा है, लेकिन उसमें मालूम है कि वो बिगड़ते जा रहा है.